Okay, I guess we should start now. George, can you confirm that everyone can hear me and see my slides?
Yes, Andrea, I confirm that the
Okay,
slides are visible and the sound is all right.
okay, perfect. Yeah, if something is not okay, then you can unmute and so. Okay, hello everyone. Welcome to the sixth edition of the Mobile AI Workshop. My name is Andrei Ignatov, and first of all, I will say a few things about logistics. So the main event now happens on site at CVPR in room 505. Also, some of the participants are attending this workshop online using Zoom link. This workshop is also streamed live on YouTube. So if you would like to watch again some of the presentations, then you can later go to our YouTube channel. The recordings will be available there. And as always, the key topic of this workshop is very practical. We're interested not just in some theoretical performance of models, not in some plots that are often not correlated with the real runtime that you can get on actual devices. We're interested in how we can deploy models on mobile hardware. We're interested in how to optimize these models so that they show the best possible results on actual mobile accelerators. And of course, we're interested on how to run these models on dedicated AI accelerators. Because as we know, modern smartphone NPUs, and not only smartphone NPUs, they can provide up to 50 or 100 times speed up compared to CPU and GPU-based execution. So of course, if we want to deploy some model on mobile devices, we would like to use this NPU. And this is, as I mentioned, the sixth edition of this workshop. The previous editions were also recorded. So on YouTube, you can find recordings for year 2021, 2022. These are a little bit old recordings, old talks, but if you are not familiar with this field at all, you can check some of the videos because some of them are still relevant. And it's what is more important is that previous year recording is also available on YouTube. And this was quite extensive recording. So for instance, in last year, I gave a 2-hour introductory talk where I tried to cover almost all basics related to deployment of neural networks on mobile devices on smartphones. In particular, I've talked about all software options of all libraries that can allow you to run neural networks on mobile devices. We discussed what options should be used, what options should be ignored. We also talked about hardware. I provide an overview of pretty much all neural accelerators from year 2015 to the latest years, and we checked briefly the aspects. We talked about their performance, and so that you can understand what kind of results you can expect when deploying models on different NPUs from different generations. We also talked a lot about power consumption, about why this matters, and about the comparison of the recent smartphone chipsets in terms of power consumption. And we even covered the topic of NPUs that are present not in mobile devices, but are embedded into processors available for laptops, desktops, and some other hardware. And we talked about how their performance relates to mobile devices. And yeah, basically the main outcome is that on mobile devices, you can get much better results than on NPUs from laptops or desktops. And therefore, if you know how to deploy your model on your mobile device, then you should not have big issues in deploying it on other constrained hardware. So all topics covered last year, they still make a lot of sense. They're still relevant. So if, again, you are completely unfamiliar with this field, I strongly recommend you starting with that 2-hour talk. And today, in the introductory talk, I will briefly cover the updates in mobile AI ecosystem that happened during the last year. Yeah, the situation is that this year was primarily evolutionary. So we have only evolutionary updates. So there are no radical changes. There are some minor updates in software, AI ecosystem. There are also new chipsets released by mobile vendors. Yeah, but there are no like huge steps compared to the previous year. So in this presentation, I will just go briefly make a brief recap of the most important points from the previous year and tell you about a few updates. So after this talk, we'll have an invited talk from Alex Baum, who is Senior Director of Product Management in Qualcomm, and he will tell you about the challenges, the goals that Qualcomm sees when it comes to deployment of neural networks and computer vision models on edge devices, and will also provide you with some hints on how to efficiently execute models on Qualcomm hardware. And then we'll talk about challenges. So I'll present top solutions and the results of the challenges that happened in conjunction with the workshop this year. There would be several paper presentations for top solutions from these challenges, and there will be also a number of extra presentations of the papers accepted in this workshop, where the guys presented some models for efficient neural architectures or for efficient deployment of these models on mobile devices. So we'll start now with software. And again, I will first give a brief recap and say a few things that changed since the previous year. So as you know, we cannot run PyTorch or TensorFlow models directly on mobile devices. So if you train your model and you want to deploy it on your own smartphone, then you need to export it for mobile inference to an appropriate format, and then use the corresponding mobile machine learning library to run this model on a smartphone or another mobile device. And the question is, what libraries should you use? In general, if you try searching for different options, most likely you will find these four options. These are the primary options. It's LightRT, which is Format Flight framework. It's CoreML for deployment on iOS. It's ExecuteTorch, and it's Onyx. So we talked quite a bit about these frameworks last year. Now, again, just a brief recap. What should you choose and what should you not choose? So Onyx library, you shouldn't choose it for deployment on Android smartphones for a very simple reason. It offers only CPU-based execution of neural networks. So if you use Onyx, then you can run it on mobile CPU, but you won't be able to accelerate this model on GPU or on NPUs. And therefore, this library doesn't have, in the context of smartphones, in context of Android smartphones and Apple smartphones, it doesn't have any advantage compared to other options. So you can just ignore it. Then we have ExecuteTorch. And we also cannot recommend using ExecuteTorch for another reason. 1 second. Okay, so sorry, I had to admit the guys waiting in the waiting room in our Zoom channel. And yeah, if George, if you can take care of this, it would be great, because there was a few guys waiting. Okay, so moving back to the presentation. So ExecuteTorch, unfortunately, it has one major drawback. With ExecuteTorch, you cannot deploy the same model across different devices, across different platforms. With ExecuteTorch, you need to compile the model for each specific platform. So if you want to run, let's say, the model on Qualcomm-based devices, you first need to compile this model for with QNN to be compatible with Qualcomm hardware. And you won't be able to run this model on MediaTek hardware or on other devices. And vice versa, like for MediaTek, you need to do the same. And even to accelerate the model with GPU, you also need to compile this model with Vulkan. And this creates problem that you basically cannot use one model and run it across different devices. Even worse, you cannot use the same executorch library to do this. So you need to, on Qualcomm-based devices, you need executorch build compiled for Qualcomm, for Qualcomm devices in case of MediaTek, executorch built for MediaTek devices, and so on. And yeah, because of this, it's not possible yet to make easy deployment with executorch. And in this case, yeah, this raises a question: why should you, in general, use executorch if you can just use vendor SDKs that will anyway provide you with better runtime and better flexibility? And we, honestly speaking, we don't see an answer to this question. So, like in case of executorch taking into account all other issues related to model conversion and its usage, yeah, its applicability is right now is content. So now the next option is Coramel, and Coramel is something that you definitely need to use if you deploy your models on iOS or macOS systems. The reason is that, yeah, first of all, it's very easy to convert models to Coramel. You can just take whatever PyTorch or TensorFlow model and just install Coramel tools through Python pip, and then you can easily get converted model. And of course, yeah, the major advantage is that it gives you the best possible runtime on Apple hardware. So with Coramel, you can run the model on Apple Neural Engine, on Apple GPU, on CPU, and in all cases, you get much better results than with any other library. For instance, Onyx also provides Coramel execution provider, but it performs like few times worse than plain Coramel. So again, if you want to deploy something on Apple, it's just Coramel and nothing else but Coramel. And then if you want to deploy something on Android devices, then your primary option is LightRT. And yeah, so this library offers quite extensive functionality. During the past 2 years, this team developed very efficient LightRT torch converter that can basically convert any PyTorch model to TF-Lite form. And using this converter is quite easy and quite straightforward. So in general, you can just use these few lines of code to get your target TF-Lite model. So you just initialize your PyTorch model. Optionally, you can swap the format of this model to channel last, and then you just export this model, and that's it. And you are getting model. This conversion works even for complex architectures. In the majority of cases, you can even convert transformer architectures and get a valid TF-Lite file. Moreover, it's also possible to get an appropriately quantized model by using extra options. So it's possible to hook up old TensorFlow quantization toolkit, and this quantization toolkit is the best that you can get right now. So unlike many other options that generate models that are not completely converted, not completely quantized, so this means that you have quite a number of quant ops in the models that will significantly slow down the inference or will result in models that are completely incompatible with quantized-only NPUs. This option, just in this simplistic way, will give you a model that can be executed on any integer age NPU. And again, the only difference from the previous snippet is that you need to add this flag and mention this flag when you are exporting the model. And then you'll get perfectly quantized int 8 or int 16 model. So this was about model conversion. And yeah, so the main advantages of LightRT is that, again, you convert the model only once, and then you can run this model across all platforms, unlike with executorch and some other libraries. So in this case, you just got whatever your transformer model, and you can run this model on CPU, on GPU, or on NPUs from different vendors. You don't need to modify this model. And the second major reason is that you can accelerate this model on different platforms by adding delegates. These are basically LightRT plugins that allow you to run this model on custom NPUs. and you can add as many delegates in your application as possible, as you want. And yeah, because of this, you can just have one application and enable these delegates on the fly, depending on what hardware is used for execution of your application. So that's very easy, very convenient, and yeah, because of this is the most useful tool right now. Yeah, besides that, this library also offers quite good GPU-based inference backend that can support the majority of architectures and, as I mentioned, good composition. So when it comes to delegates, again, the main options that you have are lighter T GPU delegate. It allows you to accelerate models on GPUs, on mobile GPUs, and it supports almost all mobile GPUs. So the requirements are very low, so you can pretty much execute this model on any smartphone released during the past 10 years. And you can, and this delegate can use almost all RAM available on mobile device. The second primary delegate is Qualcomm QNM delegate, and as you can guess, with this delegate you can accelerate your models on Qualcomm NPUs, on Qualcomm Hexagon Tensor processors, and again it supports all chipsets released during the past few years. And for MediaTek, you should use MediaTek Neuron delegate that also supports Dimensity chipsets. Well, mid-range and high-end, low-end Dimensity chipsets unfortunately not supported. So yeah, these are the three main delegates. You can recall that, for instance, last year I mentioned some other delegates. Yeah, unfortunately, many of them are already either outdated or deprecated. So, for instance, there also exists Hexagon delegate that was deprecated a while ago, with which you can run models on old Qualcomm Hexagon DSPs. There was also Armonem delegate that was deprecated also 1 year ago. And yeah, there was RML delegate that was developed by Google and which performance was completely terrible. So again, it's quite unlikely that you would need these delegates. You can still find older releases of those delegates and use them, but there is pretty much no use of them right now. And the last thing that I would like to mention here is that there exists two separate branches of lighter T. So there exists branch 1x and 0x, and this branch, it corresponds to old lighter T library, which is basically just renamed TF-Lite library. And all things that I've just mentioned, they are related to this old branch. So this branch, it supports all previously released delegates, or legacy delegates, it supports everything. And this is something that you would like to use most definitely. And you can also see that, well, here you can see a download, the number of downloads. So you can see that, yeah, old versions are still most popular, and there is a very good reason for this. And the reason is that branch 2.x, it's despite the same name, despite the fact that it's also called lighter T, it's actually a different library. So it has a different API, it has a different strategy of working with delegates. Delegates also had to be rewritten for these newer versions, and these delegates are still in experimental phase. And actually, almost everything here is in beta phase. So if you would like to use the lighter T 2.x, then you would most likely participate in some beta testing done by Google, because lots of things are subject to changes here, and many things are not working. And again, old delegates are not working with lighter T 2.x because the mechanism is absolutely different. So you need to use only the latest beta delegates from Qualcomm and MediaTek, and other options would not be available. So again, most likely, if you want to run something on mobile device, just use lighter T 1.4 version or some earlier builds. And use 2.x only if you know why you are using it, or if you want to experiment a little bit with lighter T. So that was it with the software part. Now a few words about hardware. So during the past year, all vendors presented their new flagship SoCs. And let's say the situation is here positively boring, because yeah, everything here is exactly as expected. So Qualcomm and MediaTek released their new 8-bit Gen 5 and Dimensity 9500 SoCs, and they perform good as expected. They are the best what you can get on the market in terms of NPU performance. Then you can get, then yeah, Apple released Apple A18 Pro, and it features basically the same, almost the same neural engine as previous generations. So there are only minor changes and minor performance boosts. Google Tensor, yeah, everything is also as expected. It performs as bad as previous generations, and yeah, its results are on both software and hardware side as bad as they were before. So it basically lags few generations behind what you get from solutions from MediaTek and Qualcomm. And yeah, this unfortunately not only this is not only related to its Tensor TPU, but also it's related to GPU and CPU that yeah cannot stand the critics and that have lots of major flaws compared to current SoCs from other vendors. And here I also didn't mention something Exynos chipset because you cannot accept, because yeah, NPU delegate is not publicly available, so you cannot access its NPU anyway. And I didn't also mention various SoCs from Huawei, because with Huawei situation is even worse than with Google. So software and hardware support is pretty much inexistent for the NPU, so you can just completely ignore these two chipsets. And yeah, finally, we are moving to benchmarking. So as always, we're using a benchmark application for testing the performance of NPUs. This application was first released in 2018, 8 years ago, and it basically evolved along the evolution of mobile NPUs. And for testing, yeah, it contains quite a number of different computer vision and natural language processing models, and it runs these models on NPUs using lighter-T and lighter-T delegate in case of Android devices and Caramel in case of Apple devices. And it benchmarks various NPU performance aspects, including throughput, including accuracy, initialization time, memory consumption, power efficiency, and so on. So here you can see the models that are used for testing. So this covers quite a number of different fields, including classification, segmentation, depth estimation, LLMs, stable diffusion, image-to-image mapping, and lots of architectures within each section. And yeah, when you run this model, you can see visualization of model outputs. You can see what the models are doing, and at the end of the test, you will see detailed results for every model. You can see its runtime on CPU, on NPU. You can also switch between different backends, and let's say you can run all tests when using GPU, or you can use different delegates and see how their performance compares. So yeah, it provides quite a number of different options for developers and for enthusiasts. And yeah, finally, a few words about the ranking. So here you can see the ranking table, the current ranking table for smartphone SoCs. Again, as I mentioned, top results are demonstrated by Snapdragon 8 Elite and Dimensity 9500 SoCs. Their performance is very close. And they outperform all other chipsets by vast majority, by a huge margin. Below you can see basically SoC, well, previous generation SoCs from the same vendors, and yeah, Apple A19 is also performing quite good, yeah, and we cannot see here neither of Google Tensor chipsets or some other chipsets for the reason I described before. And yeah, these are aggregated results. If you are interested in detailed performance metrics, you can just press on the View Detailed Results button, and then you can see the runtime of every single model on every single chipset. So for instance, here you can see that Swing Transformer, the runtime of Swing Transformer is 2.4 milliseconds when you run it on Snapdragon 8 Elite Gen 5. SoC and 2.8 milliseconds on the same NPU if you're running a floating point model and not quantized model. And these results are available for all models. You can just check how each NPU, each SoC can accelerate every architecture and how efficient is it in handling this. So yeah, if you are doing development, if you are developing new architectures, you might find this useful, as these results provide quite a lot of insights on what can be executed efficiently on mobile devices and what results can you expect. And yeah, besides these results, you can also find the results for smartphones. You can also find the results from IoT boards, for IoT chipsets. So yeah, I hope you can find these results useful. So, and now I'll be wrapping up. So if you are interested in developing new architectures for mobile devices, you can also check the results from the previous competitions that took part in the previous mobile AI challenges. So you can, on the same workshop webpage, you can find challenge records for competitions that happened in year 2021, 2022, that happened previous year, and in all these reports we describe all top architectures proposed for these competitions, and again provide the evaluation of all models on real hardware. So you can see that, for instance, last year we checked the performance of super resolution models on Google Tensor TPU. For other models, for other competitions, we use just mobile GPU, so you can find this information. And yeah, today I'll also present the results of this year challenges on a couple of computer vision topics. You can see also the target platform that we used for benchmarking these challenges on this slide. So yeah, I will show you briefly the results and top solutions in this competition. And with this, I end my presentation. So if we have some questions, maybe we have time for 1 or 2 questions, if there are any. And otherwise, we'll move to our invited talk. I see that Felix has already joined the workshop. Has already joined Zoom. So yeah, are there any questions? So again, people who are watching us in Zoom, you can write your questions in the chat. For all guys attending on-site the conference, for the guys who are now present at CVPR, you can just come and just ask your question in front of the laptop, if you're not scared.
Can you hear me?
Yes, I can hear you.
Oh, so I have a question. So in our lab, we make some very exotic computing memory devices with completely different acceleration capabilities, memory allocation schemes. So if we want to support others their models and to put inference on our chip, are we better off implement a light RT delicate, or we go with the execute torch and try to set up a flow for compiling for our platform? Which path do you think is better?
Well, if you have very custom options, then it's difficult to say something concretely unless you are really experimenting a little bit with your hardware. But yeah, and again, I don't know exactly the specs of your hardware. So if you are interested, you can just write us an email. We'll check your case and maybe we can give you some advice.
Thank you.
Okay, so do we have any other questions on site? Okay, if not, then we are moving to our invited talk. So right now, Felix Baum will give a presentation about Qualcomm. About Qualcomm view on challenges and optimizations needed for edge devices. Welcome, Felix. You can, okay, 1 second, I should stop sharing the screen, and you should be able to start sharing.
Sounds good. Can you hear me?
Yes, we can hear you.
Awesome. Let me share my desktop and we'll get started. All right. Share. All right. Hopefully you can see my desktop.
Yes, we can see and we can hear.
Excellent. All right. Well, first of all, thank you everybody for giving me opportunity to present to you. Glad to be with you on this beautiful day in Colorado at the CVPR. And for those that probably forgot, the CVPR is a conference for computer vision and pattern recognition. And I personally feel that a lot of the traditional and even agentic AI-based use cases, whether it's a mobile phone or not, are starting with a camera and computer vision technology. So in this session, what I'll do is I'll kick you guys off at this workshop with trying to jump up your interest and get you start thinking about all the different use cases that you can build, the challenges that you're solving that were covered, all come together to enhance user experiences. And what we'll do is I'll walk you through some of these mobile phone experiences. I'll briefly talk about some adjacent markets. Like these days, we see a lot of XR, VR, AR type of glasses that folks utilize. So I'll talk a little bit about that. And then finally, I'll wrap up the options by talking about options that you have to build devices. And George kind of stole a little bit of my thunder, actually asking his question, because yes, Qualcomm supports both LiteRT and Executorch and our own software stack to help your models to run on our devices. So with that, let me jump straight in the deck. And at the heart of our edge devices, obviously Qualcomm has NPU, and ours is called Hexagon NPU. And my team is responsible for the software for that NPU to make sure that it runs computer vision, AI, and other algorithms that take full advantage of that hardware engine. Now, while our NPU is the main workhorse, purely due to its performance per watt, again, one of the things I want to remind you is the cell phones or glasses or other devices, they're all battery powered, and people are very, very worried about how long that battery will last. So we are trying to run these use cases and run these experiences and algorithms on a hardware backend, a hardware engine that is the most power efficient. But having said that, that NPU is our main workhorse. We do have workloads that use GPUs and CPUs and even the sensing hub, which I will cover later on in my presentation. This is particularly important because a lot of the use cases that we see customers deploy utilize multiple concurrent workloads. So you have to kind of spread your workloads and run it on every hardware backend that is present in the system. If you one of the lucky folks that purchased a phone this year, then there's a really good chance that you have all of these applications and use cases deployed on your device. In this particular case, I just took the information from Samsung website for the Galaxy. Oh boy, I apologize. For the Galaxy 26. And what you have here on the Galaxy 26, you have this agentic multi-agent that helps you to coordinate device with the cloud. You have a file overview and search applications that help you to go through your old pictures and your old photos and sort them and help you to find information on your phone very, very quickly. You have a photo assist that is NPU driven on device photo enhancement and a generative edits capability. You have a camera coach. When you start trying to take a picture, it will make suggestions for you on how to tweak the camera settings to make the camera take the perfect image. And trust me, I need that a lot when I take my selfies. Obviously, you have call screening capabilities, the night photography and video features. There's a capability on some of the phones where there's a set of algorithms that were built specifically. I laugh about it, but they were pretty much like, hey, if you're trying to take a picture or selfie with your girlfriend late at night in the bar, use these settings. type of applications. Obviously, gallery search and then the best take, where you can have a multiple images taking with expressions, and then out of the burst photos, they'll suggest you the best image based on some of the selection criteria. Again, these are just some of the use cases that we see being deployed. Obviously, there are more. And I want to kind of connect the dots between some of the challenges that you'll be working on as part of this project to some of the apps that we see being deployed on these devices. But one of the things that we see is a lot of these use cases start with images. You take an image and then you improve an image, you analyze an image, and then you'll have to quantize your model into other things. But these days we see trend of folks kind of migrating away from traditional models, traditional computer vision, bokeh effects, and other algorithms to try to take advantage of the Gen AI models. And these Gen AI models started as a text only, but these days they added text, they added image, they added audio, and obviously these new multimodal Gen AI use cases bring in additional challenges. Because obviously the models are large, so you have to quantize them. You have to make sure that you have to calibrate the image. And because these models are very, very large, there are a lot of quantization challenges that our developers have to go through to be able to fit these models and applications into the small memory constrained and obviously battery constrained device. Those AI agents, Gen AI multimodal use cases, a lot of them turn into this agent and AI assistants. But they are not just about voice and text interactions. So for the very first time, we see that everything is completely processed on your device without having to go on a cloud, and your device sees what you see. Now, you can point device at the object and interact with a camera live view, and you can ask questions, and it will be actually pretty good at answering and commenting on some of the things. Where, for example, in this silly use case that I have, is you can kind of point at the screen and ask the question, and the model actually does a pretty good job, and an app does pretty good job at responding. But this is just a starting point. Now, taking this to the next step, a lot of us, and some of you probably traveled to the CVPR, so you have to go into expense reports, you have to take images of your receipts, and your imagination is the main limit on how far you can take and your use cases. For example, this example that I have is you do expense reports, you take pictures of your receipts, your phone has access to your payment because probably using Apple Pay or Google Pay to pay for your restaurant bills and other activities. Well, it can actually do analysis, and it can go and look at everything that you've done and be able to go and make suggestions on how to split the bills or how to save some money and do a little budgeting to help you guys collect money and buy a new car or a house. Again, these are just some of the examples, some of the silly examples, but at the heart of these examples is ability of the camera to see an image, to take that image and then analyze that image and do different things with an information that it extracts from that image. Again, I think what we see with these AI assistants is not only they're processing images with a photo, but they also have ability to process voice and audio and also text. With the challenge that we see these days is be able to expand the context window, so it can actually utilize additional context for making responses and making suggestions and analyzing and improving the competency of the assistant and an app. All right, let me see if I can jump to the next slide. All right. So again, I started with some of the mobile use cases to show you what we see being deployed on devices. But these are all what I call active use cases, meaning your phone is on, you are running your application, you are pointing your camera, you are taking an image, the phone is on, the CPU is on, the GPU is on, the NPU is on. But there is a whole series of the use cases and capabilities on our devices that are also camera-driven, that are, as I call it, ambient. And this is where some of the hardware that Qualcomm has actually combines sensor, connectivity, location, and a vision in what we call the sensing hub or low-power AI engine that is actually operating at a very, very little power in an ambient mode. And it provides you with ability to do things when the CPU is off and NPU is off. You can kind of call out your device and ask questions to it or have that wake up the phone. So again, I started with the mobile devices. I talk a little bit about ambient use cases, but a mobile phone today is kind of the main phone-centric tethering device, so to speak, to which a lot of the devices that we see users deploy talk to. For example, you have the Ring, Aura Ring, or Samsung Ring that talks to your phone. You probably have, just like me, a smartwatch that talks to your phone. You have earbuds that talk to your phone, and then you have glasses that probably talk to your phone. But what we see is the glasses use images, the phone and the watch and the Ring use sensing information, and they're all feeding into the phone where you have an app running to combine all this information. We see a large transition of these use cases. Where are they migrating from being kind of phone-centric to being human-centric and AI-centric, where you're wearing a watch, you're wearing a phone, you have a phone in your pocket, but your watch and your Ring and your glasses actually talk to your agents, talk to your apps, talk to your assistants, some of them running on device, some of them running in the cloud. I briefly touched a little bit on that, but we see a lot of transition where people are more and more adopting these glasses as a technology to interact with the world, where instead of you carrying a phone everywhere and having to point a front camera or a back camera to what you want to interact with and understand what is happening around you. We see more and more a convenient trend where people utilize and wear glasses. And the glasses combine a lot of the computer vision and camera-based technologies because they have to use cameras for hand tracking. They have to use camera algorithms and computer vision algorithm for facial tracking and head tracking. Obviously, to understand where you're looking in the world, they have to run computer vision algorithm to understand eye tracking. There's obviously a see-through where you're looking through the camera and the camera takes an image, so you have to understand what's happening in front of you. There's some additional challenges that are coming in with a 3D mapping. And then obviously recognizing an objects in front of you and tracking those objects. Again, all of those things come together in a glasses form factor devices. And you have to understand that those devices are much lighter. They have much smaller memory and they have a much smaller battery. So all the challenges that I kind of talked to a little bit about mobile phone form factor type of use cases exacerbated even more if you think about a glasses form factor type of device. What we do see is these glasses becoming popular because it is the most natural way these days to interact with these assistants, where you can talk and your glasses have microphones and they will understand what you're trying to do. You wouldn't have to go pull your phone out of your pocket. press a bunch of buttons and run an app and do other things. You can just literally talk to your agent running in the glasses, and it will see what you see, and it will execute your commands on the mobile phone or in the cloud. We see a lot of contextual awareness, where in this particular silly example, which actually very relatable to me, I don't know if you can see camera behind me, but I have actually dying plant behind me, is there's a contextual awareness. You can look at the plant, and the app would go and understand what you're looking at. It would run image processing software, understand what it is. It will go to the cloud, and then it will give you hints of, oh, well, gee, I better go water my plant or do something else with it. And then obviously simple things like OCR type of algorithms, where you're looking at the text, you're reading a book, and it can help you with the problem solving and reasoning, and learn your preferences as well and history. Again, just a few use cases that I'm trying to kind of walk through briefly to help you to understand how the challenges that you're going to go through today relate to real use cases and the real devices in the real world. All right, a few other things I briefly mentioned at the beginning, that we have NPU and Sensing Hub and GPUs and CPUs, but this is kind of an example of why concurrency is super important. In this particular example, you don't just run hand tracking or head tracking and then turn it off. At any given time, you're running multiple perception technologies to track both the user, the environment, controller tracking and motion tracking, and maybe you're running, you're doing a TikTok video and you have an avatar, or you're playing a game. So this is just some of the things that you have to do concurrently if you are building a real life use case utilizing some of these computer vision technologies and algorithms. All right, so what do we do at Qualcomm to help with that? So some of the things that we do is we try to optimize for power and try to combine a number of these technologies and shrink not just processing from the performance perspective, but also shrink it from the power perspective. This particular case that you see example is that you have this video see-through example where you have to take an image from a camera, you have to do lens correction, you have to wait for the frame to come in, you have to render your frame, you have to display that frame, do warping or dewarping, and then push the image to the display. This is kind of traditional pipeline. And what Qualcomm has done is we harden a lot of these capabilities that allows us to take an image from the camera, do everything in one shot, and then push everything to display at once. And you can see the savings in time that it takes us to process that same frame. And that immediately translates into the amount of power you can save by doing so. All right. Again, another example is here. What we have is our cameras in a lot of our phones and glasses support 14-bit dual ISP for really great image quality, where you can get up to 12 megapixel for photos, 6 for videos, all in a glasses type of form factor. And this next generation smart glasses truly built to bring cutting edge technologies. Let's see. Now, they're combining features such as auto exposure, auto face detection. Again, I'm just reading some of the things that we do there, and HDR and portrait mode. Now, I feel that, and I actually have some of these devices in my office here. They're truly going to revolutionize how we interact with our assistants and with our devices going forward. All right. Again, just a few last points for this is computer vision is just portion of that. Obviously, when you think about these glasses and phones, it is super important to combine the computer vision aided audio and video captures deal with a noise cancellation, support voice commands, visual search, and obviously health data if you're wearing like a ring or a smart watch, and then be able to support this health sensor for fitness tracking, which is something that folks do these days a lot. Now, where does Qualcomm comes in? So Qualcomm has developed a number of different hardware platforms that, as I mentioned before, combine the CPUs, the GPUs, NPUs, sensing hub or LPI type of hardware engines. These hardware platforms span from mobile phones, automotive devices, computers, like for example, my computer is a Snapdragon-based device with an NPU in it. Glasses I talked about as well. And then we have a number of SoCs that go into the robots and data centers. And what we do for that is on top of the hardware that we built, we deployed end-to-end software for it, supporting all popular runtime frameworks and delegation to our hardware backends. So back to the questions that I think George asked. Yes for PyTorch, yes for TensorFlow. Yes, we support Windows MLs as well and Onyx and things like that. Now, we have frameworks in place for agentic use cases, and then we provide customers with tools. And these devices run various operating systems. So yes, we support Android devices and Linux devices and Zephyr-based and QNX for the folks that are building automotive devices as well. So the stack that we provide and ship to our customers, as I mentioned, allows you to take your model that was built using TensorFlow, JAX, PyTorch, or Onyx. We support, obviously, Qualcomm runtime framework, but we also support other community-based frameworks. But the one thing that you might not know is we also provide a number of other libraries and languages. So if you're running computer vision algorithms, we provide equivalent to the OpenCV libraries. If you're using math, if you're utilizing math libraries, we provide optimized math libraries and routines for our hardware backends. We provide with container technologies if you're trying to virtualize things and protect things. We obviously have emulators and different compilers that allow you to generate super efficient custom operators or computer vision algorithms. And then we provide system software, interfaces, drivers, inter-process communication techniques and technologies to help you to talk to our hardware backends directly. So one of the things that we do, kind of trying to drill down a little bit on opening the hood, is we allow you to, as I said, build models using PyTorch, TensorFlow, or Onyx, and come to Qualcomm. We distribute Qualcomm AI runtimes. That is an SDK that includes model conversion, model quantization, model compilation tools, and everything else that you would need to take your AI algorithm and run it on any one of these engines. We also understand that quantization is difficult, and folks have sometimes trouble trying to quantize the model and calibrate it to driving all the way from floating point to in16 to 16 by 16, 16 by 8, 16 by 4, 8 by 8, 8 by 2, 8 by 4 type of data types, and also mixing and matching them. So because quantization is difficult, what we've done is we have our own model zoo, so to speak. We call it Qualcomm AI Hub, where we already have a number of different pre-quantized models that are there for you. And as a matter of fact, you can go to AI Hub today, grab a model, grab a runtime, specify if you want to use CART or any other community runtime, pick a hardware, and very quickly run your model on device and see how it performs and how accurate it runs. So this is something that Qualcomm natively provides. You can come to our websites and we give you all of the tools available. They're all available to you. And we don't make different version of the tools. Exactly the same set of SDK and tools and technologies that we provide to third-party developers and grad students and college students is exactly the same software that we deliver to our paying customers and OEMs and partners. Now, alternatively, we work a lot with community. And this is where if you come from TensorFlow or if you come from PyTorch, you can deploy your model on our devices using either LiteRT runtime or ExecuTorch runtime or Onyx runtime. Again, the way I look at it, if you start with a PyTorch and you end up with a Qualcomm NPU running your model, it shouldn't matter to us which path you took. You took a path of Qualcomm proprietary software, or you took a path of one of the community-based runtimes. We try to make it as simple, as easy as possible for you to get there. In fact, one of the things we do with both LiteRT and ExecuTorch, we upstream everything that a developer would need to allow you not to even worry about Qualcomm capabilities. So if you go to LiteRT repo, if you go to the ExecuTorch repo, you don't have to then go to Qualcomm to read our documentation, to go to Qualcomm and download our libraries or our compilers or anything else. We upstream everything up. We publish all of the necessary documentation in those repos. So you go to the LiteRT repo, you go to the ExecuTorch repo, and you have everything that you need there to be able to build your model and target any one of our hardware platforms. Again, what we do on the back end is we integrate our hardware delegates into those frameworks, and we work very closely. I think this slide is, I give up on trying to keep up with the slide, trying to put newer models, newer technologies, newer capabilities into it. But yes, we enable a whole bunch of different models. And if you can find a model out there, there's a really, really good chance that it already been deployed by somebody on one of our SoCs. If you invent your own model, or if you have your own way to enhance your model, what we do is, whatever it's a Qualcomm runtime or LiteRT or ExecuTorch, we support what we call capability called custom op, where you can take your computer vision algorithm or special kernels and integrate it into those runtime frameworks and expand these models. So for example, you can start with a mobile bird, add something before, or add something in the end, or add something in the middle, and compile this end-to-end model and deploy it on our NPU utilizing this custom op capabilities. This is just one of the examples that I took because a lot of these models these days are built using PyTorch. If you start with a PyTorch, obviously you can convert it to use Qualcomm Card SDK or LiteRT workflow. But if you want to stick with your PyTorch, so to speak, workflow, you start with your PyTorch module, you do Torch Expert, you get the HIR, intermediate representation, then you go and apply the ExecuTorch ahead of time transformations, end up with ExecuTorch partition in a package, which is pretty much .pte file. Take your .pte file, make it part of the Android app, and then when you run your ExecuTorch runtime, you pass your .pte, lo and behold, and it executes on our whichever hardware backend engine you're going to target, whatever it's going to be, a CPU, a GPU, or an NPU. So this is a hardware agnostic pipeline. I could have built the same diagram, similar diagram for LiteRT, but we here at Qualcomm on the software side make sure that we support all of these runtime frameworks and all of these different operating system, whether it's an Android example or Linux. So just to wrap things up, again, I appreciate Andrew giving me this opportunity to talk to you and kind of pitch Qualcomm capabilities. But yes, we have devices that we built all the way from doorbells to data centers with glasses, with mobile phones, with a compute form factor. I used in this session just a mobile phone factor and a glasses just to kind of spark your imagination, to show you how some of the challenges that you're going to be solving here help with the real life examples. And good luck to everybody on this call with the challenges. Really looking forward to your submissions to see how you solve the problem that Andrei listed in a previous session. With that, thank you, everybody. Andrei, you still here?
Yes. Well, it would be strange if I would not be here. Yes, thanks a lot for the wonderful talk with lots of also technical details. It was really great to hear all these insights, all these suggestions, yeah, all these overviews. So I think, yeah, probably the next competition should be on LLMs for smart glasses.
Sounds wonderful.
Yeah.
We can definitely have a session and talk about what are we doing with all these llamas of 2 years ago and Gemma 4s of today's, and show you how they could be used for image processing and how they enhance your use cases.
Yeah. So are there any questions to Felix?
I think we have a question from the audience in here.
Yes.
Hi, very nice talk. I have a question regarding the runtime frameworks. What is the one that you feel is more mature actually for the users? Is it executors, INRT? Because we see these are quite new, and sometimes developers are kind of struggling to see which one is best fit because it's under heavy action development at the minute. Yeah.
I'm trying to be Switzerland, and I know Andrew is laughing because I know where he's located, but what I do see is if people build things for compute form factor type of devices, they usually go with the Windows ML or Onyx RT. I see that a lot of times when people build for the Android type of devices, they probably want to stay within an Android and Google ecosystem, so they probably pick LiteRT. I think that a lot of folks come from PyTorch, and because of that, they stick to Executorch. And we've been working with Executorch for the last few years. And I think that our enablement and support within Executorch is really good. It's hard to answer your question because sometimes it's almost like a religious battle. It's like Christianity versus Islam versus some other religion, right? Judaism, right? I try not to suggest which one is better. We enable them all, but yes, you are absolutely right. I think if you look at the maturity, obviously ORT has been there for a couple of years. Obviously Executorch launched 1.0 version at the last PyTorch conference last October, but they've been pushing Executorch and working with the community for at least 2 years with the beta and alpha products. LiteRT, you're absolutely right, just went through the large transformations. There used to be TensorFlow that used to be dated and didn't support GenAI use cases. So Google took axe to that runtime frameworks and shipped LiteRT within the last few quarters. So it's newer than anything else out there, but they did a pretty good job at making sure that it supports out of the box GenAI and traditional use cases. That addresses the limitations that they had with a TensorFlow, where it used to be JIT, just-in-time on-device compilation workflow. So now they support it ahead of time. So again, I almost feel that a lot of these runtime frameworks kind of try to match each other in features and capabilities. And whichever one you prefer, we'll be more than happy to work with you on that and talk to you about what we're doing there, what support we have, data types, features, and capabilities. So let the best runtime framework win.
A very nice answer. I have one more quick one.
Please.
So where do you see actually the chips are actually progressing? Is it on the memory side or more on the compute side in order to support actually larger models and better models in the future? Where is the
All right.
chip
So very good question. I think that let me kind of separate things. First of all, for the vast majority of the computer-based use cases, computer vision-based use cases, like a camera-based use case where I'm taking a selfie and everything, what we see is there are a lot of models that are being used that are kind of smaller, and this is where people try to use multiple concurrent models. So this is where the memory is not such a big problem. It's concurrency that is a problem for a lot of them, because you're trying to run a whole bunch of things before the next frame comes in. And some of the use cases we've seen in a camera where they're running 26 different models before the next frame comes in, so they can enhance the image and balance the whatever the intensities and everything else to make a person look good and the skin look radiant and everything else. When we talk about Gen AI, up until I would say a year and a half ago, I would say that compute was a problem, because these models tend to be 7 billion parameters, 8 billion parameters. You quantize them to 16 by 2 or lower data types, or 16 by 4, and then you still get to about 5 gig of model. So it's huge model, and it takes a lot of compute resources to process it. But what happened is two things. First of all, we see a big trend in these Gen AI models getting smaller and smaller. What used to be done with 7 and 8 billion parameters models 2-3 years ago, like a Llama 7B. Last year, you are able to do the same thing with Gemma 3 4 billion parameter model. The exact same set of features and capability this year. You can get away with using Gemma 4 2 billion parameters. It's as good, it's as competent, and it also supports all these multiple modalities. So I feel that the memory is not such a big deal. So they're shrinking and becoming better and better. I think right now it's all about how fast you can process it, how responsive can you do it, because people are trying to do multiple modalities. And also, you don't just run your Gemma 4. You have to take a picture, do image processing, do a few other things, maybe scrub a phone screen to analyze what you're looking at, and then run your Gemma 4 or whatever else you have running to be able to help with these agentic experiences. Hopefully that answered your question. Sorry for kind of lengthy response.
Well, thanks.
All right. Any other questions from the folks on the call, on the bridge? If not, Andrei, back to you.
Then probably, yeah, we can stop here. And thanks a lot for the presentation and for the answers. So, like, I think that for the answer regarding frameworks, we could just make another 30-minute presentation showing this, showing all this information to the guys. But anyway, it's very useful and it's very informative. Okay, so yeah, if there are no more questions, then thank you, Felix, and we'll move to the next presentation, which is an overview of our most traditional, most basic challenge on image super resolution. 1 second.
All right. Thank you, everybody.
Thank you, Felix. Okay, can you see my slides?
Yes, we can.
Okay, great, thanks. So again, we start with the most traditional challenge, image super resolution. I guess it doesn't need an introduction because it's quite old-fashioned, but still it's used very frequently. On mobile devices, as you always need to upsample low-resolution media, you need to upsample your images when you're using telephoto camera, and now all vendors are using super resolution models for this, or when you are using low-resolution videos or some other streaming data. So in all these cases, you need to upsample your input data. You need to achieve quite good reconstruction quality. And which is even more important, if you are doing this on mobile devices, you need to do this super fast. And especially you need to use NPUs, because NPUs are considerably more power efficient than any other hardware. So you get huge boost in power efficiency compared to CPU or GPU-based execution, and in the case of mobile devices with any battery, this is super critical. So in this competition, the goal was to present solutions that can run on NPUs, that can demonstrate real-time performance, and that can upsample images from Full HD to 4K resolution. So 4K is basically the largest resolution you might need on mobile devices, because no one right now goes beyond 4K. So the constraints, the targets were very practical from a mobile point of view. And as for the dataset, we use the most popular V2K dataset that provides you with 1000 diverse 2K resolution RGB images. Yeah, it covers lots of different scenes, lots of different photos, lots of different cameras. So in this case, it's quite good in terms of dataset, in terms of being used for training. Also, quite a number of participants used some external data sets. They used either Flickr extension of V2K or some other privately collected images. And they also reported that this data was used. All solutions were evaluated based on two major metrics. The first one is fidelity score, which was measured using PSNR metric and the same metric. And the second important aspect was runtime. And for runtime, we had two tracks in this competition. A quantized track, here we used Snapdragon 811.5 NPU. And for floating point track, we used an Dimensity 9500 SoC. And the final score was obtained as a combination of fidelity score and runtime score. Basically, the participants had to find the best balance between reconstruction fidelity and the runtime of these models on actual NPU. During the development phase, the participants used a benchmark application. In this application, it allows you to load your custom 10-flow light model and run it with different acceleration options. So, for instance, if you want to check the speed of the model on Qualcomm hexagon NPUs, you can just select Qualcomm QNN HTTP delegate, and it is available for all devices released in the past few years. So it doesn't matter what kind of smartphone you have. If it is using Qualcomm SoCs, then you should be able to run this model on this NPU. And then you can just run the models that you've designed on this NPU and get detailed runtime results on this hardware. And the same is applicable for MediaTek. So select just MediaTek Neuron delegate, and then you are able to run this model on MediaTek NPU. So these tools were used used by participants during the development phase. The participants had also a chance to send us their models once a week, and send up to 3 models once a week, and we provided them with runtime values on the target device. And for the final validation, we used the same setup. Here you can see the results for quantized track. The most important things that you might notice is that we had 4 top solutions that achieved a runtime of around 5 milliseconds on Qualcomm NPU. And these are dramatic results, because this means that any image, any Full HD resolution image, can be upsampled to 4K resolution on Qualcomm-based devices in around 5 milliseconds. And you can see that PSNR and the same scores for all top competitions were quite high. And especially if you compare against bicubic upsampling, then there is a huge boost. So, for instance, probably you all know this, because pretty much any CNN-based model would significantly outperform the standard image interpolation methods. But yeah, you can see that in this case, PSNR score was improved by almost 2 dB, and as the same improved from 0.82 to 0.87. But yeah, what is most important here is the runtime. That the runtime of the models proposed by anti-SP and anti-SAR teams it was even faster than when you are doing this interpolation using bicubic upsampling. So these methods can be considered as basically a default upsampling methods for the majority of mobile devices, because they give a much better fidelity results, much better visual reconstruction quality, at the same time being almost free. And you can also imagine that if the subsampling takes only 5 milliseconds when you are going to 4K resolutions, and for low resolution images it will be much lower. So if you want to upsample images to full HD resolution, it would be less than 1 millisecond, which means that you can do this almost for free. And yeah, so here you can see the overall ranking table for this competition and the results for different teams. It should be mentioned, one thing that should be noted here is that all winning teams, they were still using TensorFlow, because as I mentioned during the intro talk, TensorFlow and LighterT, they offer the best quantization utilities, the best quantization toolkit with which you can get really nice quantization results. You can see that the first two teams, for instance, achieved almost lossless quantization. So the drop from the FP32 models to NT8 models was less than 0.1 dB in both cases. And if you are using PyTorch and you are trying to do a conversion from PyTorch models to LighterT or PyTorch model to Executorch, or from PyTorch model to Onyx, then this drop is usually much larger and it can be really noticeable. And therefore, yeah, all top teams, they either developed and trained the models with TensorFlow directly, or use PyTorch for training the models and converted these models to TensorFlow and then exported these models. And then, applied additional context to their training and exported these models to LighterT framework. Yeah, and for the second competition for 14-point track, the results are somewhat different. Yeah, this track was a little bit harder because we had some extra constraints regarding the target accuracy, target fidelity of the solutions. They have to be much closer to 31 dB when it comes to PSNR. And you can see that, for instance, top solution from ZTE-CV and RTSP, they perform much better. They demonstrate much better results compared to solutions from quantized track. At the same time, the first two teams were able to develop models that are completely compatible with MediaTek MPU, and they achieved a runtime of around 100 milliseconds. And again, in this case, we are also dealing with floating point models, so this means that these models would anyway be slower than quantized models, but yeah, here you get also extra boost, noticeable extra boost in PSNR at SSAs. And yeah, so in the second track, the winners are ZTE-CV and RTSP. Now let's briefly check the models proposed by these teams. So in case of quantized track, the best model was developed by RTSP, and you can see its architecture here. The key idea is using layer parameterization. So here during training, you use multiple convolutions, and in this case, you increase the number of training parameters for the model. And during inference, all these convolutions are fused into one convolutional loop, and therefore you get an extremely efficient model that has 4 times, or not exactly 4 times, but much less number of parameters, while showing the same results, because this fusion gives you mathematical equivalent operation compared to the original block. And because of this, you're getting much more efficient model while being able to achieve good reconstruction results. So, and besides that, what was necessary is using skip connections and using quantized event training for tuning the model, and not forgetting a huge accuracy drop caused by this quantization. So this model was trained with one loss, but the authors changed the learning rates and changed the resolution of the input patches during the training process. So they had multiple stages when they switched from different training resolutions and adjusted the learning rate. So for the second track, team on TSP proposed a bit larger model. As we know, yeah, it was able to achieve much better PSNN same scores. These improvements were primarily achieved by using quite a large number of skip connections. The authors also used the reparameterization here, and the model was trained with L1. So here is the overall architecture, and one extra thing is that spatial attention was also helpful for getting better upsampling quality. So, in the second track, the winner is team ZTSCV, and you'll hear about this team in some subsequent presentations as well. So this is a team from the ZTE Corporation, and they managed to get top results in multiple competitions. So this team is very creative, and is able to design very efficient models. Here for this competition, they basically based their solution on knowledge distillation. So first they trained a much larger teacher model and then use the outputs of this model for training student model. And they use these outputs to compute an additional log. And the entire the student model was trained with a combination of one or two and self-distillation loss function. Another idea is that they used they added Sobel and Laplacian filters into href logs. So basically, these were convolutions, but with fixed values, so that they correspond to Sobel and Laplacian filters. And then again, these filters were fused into one single convolutional op during inference, and this helped the authors to get better reconstruction. Yeah, so this was the key idea behind the proposed architecture. You can find detailed results about all solutions all top solutions proposed in this challenge in the challenge report. So it would become available next week. And again, in this report, we show all results and we described in detail the architecture, all the training strategy that each team used. So you can find detailed results for all teams participating in both competitions on the website. So we stop here, and we have one extra presentation from the team who participated in this competition. One second. Are the guys online? So we are moving to the next two-paper presentation, efficient in 8 single image resolution via deployment array quantization. Are there authors online?
Hello.
Yes. So you can start sharing your slides.
Do you see the screen?
Yes. I can see the screen and I can hear you.
Okay, I will start now. Hello everyone. Thank you for joining today's presentation. My name is Lê Nam Thi. Today I'm very honored to present our paper titled Efficient Integer 8 Single Image Super Resolution Deployment Aware Quantization and Teacher Guided Training. This work was co-authored with my colleague Nguyên Phạm Phương Nam, Lê Nam Tiến, it's me, Phó Thị Kim Trang, với Như Tình Anh, representing Vietnam National University, Ho Chi Minh City. So I will walk through how we design an efficient super resolution framework that bridge the gap between high fidelity image reconstruction and deployment constraints on mobile APUs. So as we can see, we go to 5 main sections: the abstract and introduction, related works, methodology, experiment, and conclusion. I will get into Sanders' executive summary of artwork. The main problem is to tackle the scale factor 3 times single image separation. But it must recover fine details. But a low bit integer A deployment can amplify small numerical errors into visible blur, texture degradation, and edge artifacts. So our main contribution is to unify training pipeline, a compact extract refine stable student performs most computational in low resolution space that's use mobile one style reparameterizable blocks and visual shuffle reconstruction. Our model use only 82 thousand parameters, and we got a final score of 1.8. Okay. So the problem is why is this difficult? Because there are some high capacity super resolution models can reconstruct better texture, but are expensive and harder to compress. Super resolution quality is measured pixel by pixel, so routing and activation range errors can become visible artifact. For 3 times separation, the model must infer missing high frequency information while reserving accurate structure. Mobile ABU deployment requires operator compatibility, small inference graph, low time, and stable integer A export. So you can see the picture right here. It's a low resolution zoom, and our model is to make the image more better and so I have five contribution like compact low resolution space architecture. We got input stem your mobile one style blocks and a global picture skip, visual shuffle 3 times head, and redesign postpone assembly. So most compute stays at 8 times width instead of 3 8 times 3 width. So we have a teacher guided fidelity training. In stage 2 and 3, use Chaponier loss, DCT, the discrete cosine transform, domain supervision, and coherent weight output distillation. Third, I deploy the quanti-aware training pipeline. The model is first fused into a real inference graph. Then the quanti-aware training is inserted into the fused graph to reduce the structural mismatch. Quanti-decentrable stability tricks. The patch norm recalibration updates running statistics before fusion. Where clipping reduce stream values and improve low bit stability. So I will explain why those feature or matters. Because why the low resolution space matters. If the networks upscale early, every later convolution runs on a 9 times larger spatial reach for 3 times super resolution. Plane assembling is therefore critical for mobile efficiency. why teacher matters. A common student may misfind texture and no local structure. The Mamba-based teacher prediction provide richer both level solution without changing inference cost. And why views anti-weight chaining matters because on multiple range graph do not perfectly match the final single range graph. So fusion before quanti-aware chaining makes simulated chaining closer to real TensorFlow fly integer execution. So this is a student network pipeline. The mobile one block in training time. We got convolution to input and picture channels. Refine we have 8 mobile one style blocks for improve optimization. And also the feature level global skip. You have a reserve structure and stabilize reconstruction. And finally, we have an assembled for final 3x3 projection output 27 channels. Then process visual support to reconstruct high resolution RGB output. So see the training time block and the inference time block, as you can see on the screen. On the training object, we got stage 1, A1 reconstruction. It learns the stable base mapping from low resolution to high resolution. This avoid too many competing objectives before the student can reconstruct the spatial structure. We also had 2 loss, which is a Sharponer loss using stage 3 and 2 and 3 as a robot reconstruction loss. It behaves as a smooth L1 and is less sensitive to outliers than for L2. And the DCT domain blocks have a reverse high frequency components that are important for texture and edge. We have a confident weighted knowledge distribution. The teacher error is converted into a confidence weight. More reliable teacher is so bad, stronger supervision, while the teacher mistake are down weighted. So it's our formula. In the interpretation, the loss schedule gradually moves from basic spatial reconstruction to richer texture frequency learning, then to quantization of weight reduction. So this is our 3-day training blocks. As I one we will train 600 airbox where I'm to learn base separation mapping. And set to 3 to enhancement we and 200 airbox and this helps so you can look on the screen. Okay, the deployment aware training. The problem match problem is the training block multiple branch with functional and deploy block single fuse time 3x3 convolution. If the quanti-aware training is applied before fusion, the quantization noise is simulated on the graph that is not exactly deployed. After fusion, the branch level quantization effects can about unpredictably. So the solution is the patch norm recalibration calibration use of forward-only mini batches to update running statistic, multi-branch blocks or collapse to single branch, 3x3 convolution. The X is the graph mode. Anti-versioning with VNN package is inserted to the fuse deploy graph. This might affect quantized training mathematically focus closer to real integer deployment. So we have a experimental setup on the dataset in the deep 2K 3x IS as a setting for mobile AI 4K quantized image super resolution channel. We have a pre-processing, normalize, and validation. So this is our result. So this important trait of the method does not rely on a huge model. Instead, the quality is come from the low resolutions by computation. The mobile one style parameterization, teacher gather training, and quantile training on the views graph. So you see the PSNR metric. The more higher PSNR indicate that a better pixel level reconstruction quality after quantization. We also have some baseline versus the post model. So 3 methods to compare, and there are some comparisons. All right. We also test on the my mobile phone runtime on AI benchmark, and we have the CPU 110 millisecond, GPU faster than the APU is selected the fastest. The application visualization compared to the reconverse mobile one achieve the best integer infinity. We see around 30 decibel, and it also has the smallest drop from float point 32 to integer 8. So the train time aggressiveness plus deploy time fusion is better than over aggressive factorization for this tag. We also test operation visualization with teacher and the direct quantile questioning, which is improve a little. The gain is small in absolute value, but important because the threshold are strict, and even small chunk can change the final quality of the model. So the quantity visualization the microbic interpolation reduce blur and over smooth parity. Our model can reconstruct sharper edge and clearer local geometry. Yeah, as we can see, it's repeated patterns and texture-rich area are closer to high resolution ground truth. No obvious blocking artifacts or irregular edge distortion or visible after quantization. So after experiment, I can conclude that the fidelity can supply the integer A spot. The gap between strong flop-on 32 training and deployable integer A control representation training. Okay. Our limitation and future. We see that ABU runtime is not yet competitive with faster challenges. So in the future lesson, we will find the stronger lightweight backbones with better NGBU operator compatibility. So this is a final conclusion. Okay. Thank you for listening.
Thank you for the presentation. Do we have any questions? Okay, if no, then again, thanks. And we are moving to the next, to an overview of the next challenge of the video super resolution challenge. And 1 second, I'll share the screen. Okay, so I hope that everyone can see the slides. Okay, so second competition, video super resolution. So if in the previous challenge it was about upsampling just images, then here we need to upsample video frames. And yeah, so it's clear where we need this because again, whatever streaming services we are using, for instance, even if we're using Zoom, then on the actual device we would like to get image of a better quality, and there is also bandwidth limitation, so we want to transfer the original video in as low resolution as possible, and later on upsample it to overcome various issues related to connectivity. And yeah, because of this, the problem of upsampling video sources, or let's say upsample videos from any online video provider is also a quite important problem for mobile devices. Which is even more important is that with videos we need to upsample frames continuously. So the solution should be very efficient and very fast. So any solution should get at least 30 FPS speed and ideally over 60 FPS. And in this competition, the participants had to develop solutions that would demonstrate this performance on mobile GPUs. And in the previous challenge, it was 3 times upsampling. Here, we considered 4 times upsampling worked. So the participants were provided with the REDS dataset that contain target frames of HD resolution. And the dataset contains 240 videos for training and 30 for validation and 30 for testing. Here you can see an example of input video frames and target video frames. So the participants had to upsample these frames to this one. So in this, for measuring the performance of the submitted solutions, we also used Pearson and SAM scores for checking their fidelity. And runtime was evaluated on the same SoCs on Snapdragon 8 5 and Dimensity 9500, but in this case, it was measured on the corresponding GPUs, on the corresponding mobile GPUs. And yeah, upsampling was done from resolution 320 times 180 pixels to HD resolution. And the final score of each team was computed as a combination of the fidelity score and runtime. Again, the participants were able to use a benchmark for testing the speed of their models locally. For this, they had to select TFI GPU delegate option, and in this case, it was not important what mobile phone they had. So regardless of what Android smartphone you own, you can just run your TFI model on its GPU and track the progress, track how the improvements work when you introduce some optimizations to your model. and for testing we used exactly the same set. This competition was much trickier for the teams, and but yeah, we still got two excellent solutions from teams CVPR and the TechSweep. One note that should be mentioned is that the average runtime here corresponds to the runtime obtained for upsampling 10 subsequent frames. So this means that both solutions were able to demonstrate over 60 FPS when benchmarked on both mobile GPUs. And yeah, both teams are the challenge winners. They were able to obtain excellent reconstruction quality. So PSNR scores were considerably larger than the standard bicubic. Then for the standard bicubic upsampling, the same stands for the same scores. And yeah, as you can see, the runtime on GPUs was very good. So you can indeed run this model and do upsampling at 60 FPS on mobile devices. The second solution was also compatible with both 805 NPU and Dimensity 9500 NPU. So the runtimes obtained on NPUs were not taken into account when computing the final score for the models, but we anyway reported them for all solutions in all competitions so that you get an idea of this architecture is NPU friendly, and if it's possible to get an extra speed up when deploying this model on an NPU. So both solutions from teams CTCV and the TechSweep are compatible with Snapdragon's 805 NPU, and the second team also developed solutions that was also compatible with Dimensity 9500. And now let's look at the architectures proposed by this team. The TCV proposed an architecture that uses hierarchical feature extraction and fusion paradigm. This architecture contains lots of skip connections, and as we know, this is almost a must for computer vision models doing image upsampling, image super resolution. And again, this team used reparameterization to decrease the number of parameters of the model when it is deployed. And the model was trained to minimize L1 loss function, and at the end, it was additionally fine-tuned with L2 loss. The TechSweep used a slightly different approach. The key idea was to use neural architecture search to find an optimal number of parameters in their model. So first they trained the model with NAS objective to optimize the number of layers, the number of feature maps in each layer, and to get the best trade-off between model complexity and a numerical reconstruction result. And then, yeah, they additionally tuned the resulting model with L2 loss and with different training strategies. So there is a detailed overview of both architectures in the challenge report. So it describes in detail all blocks that these models are using, and also all stages of the training that the lessons performed. So feel free to check this. As I mentioned, all papers would become available online next week. And are there any questions? So if there are no questions, then we are moving directly to the third competition. Which is a mobile denoising on smartphone GPU. And yeah, so again, this topic is very fundamental, and yeah, one of my favorite ones, because the problem itself seems a little bit it seems not too complicated, because we can all easily detect noise. We understand what images are noisy, what images are noise free. At the same time, it's super difficult to remove noise, to reconstruct, to produce an image that looks like completely noise free. And even the largest models, even the most performant models, if we are taking transformer architectures, they still fail to remove noise completely in challenging scenarios. So at the same time, in case of mobile devices, denoising is needed for every single phone. First of all, because there is a separate noising step in mobile ISPs. So whenever you are taking a photo, there is noise and algorithms running on your phone to make it to make this photo look better, to remove all noise that is present there. And also, you often want to remove noise from already captured images. So in this case, you also need to work with high resolution images. You need to do the noising quite fast. And yeah, in this competition, the participants were proposed to solve this problem, and they had to design solutions that can run on mobile GPUs and the noise Full HD resolution images in acceptable runtime. As for the dataset, the participants were proposed with our in-house dataset that contains over 1,000 different scenes of resolution 4,000 times 3,000 pixels. And these images were shot in different environments, indoors, outdoors, in daytime scenario and nighttime scenarios. And to get, we had in this data set, you have pairs of images. One is noisy images and one is noise-free image. Noise-free image was obtained by averaging 20 noisy images, so that noise is averaged on. Same as in the previous competitions, numerical results were estimated using Pearson and the same scores. And for the runtime, we use the same platforms, and the runtime of these models was checked on GPUs. And the final score also combined both fidelity and runtime results. Again, for development, the participants were able to check the performance of their models on their own devices and track the progress on these devices as well. So to see whether some improvements lead to better runtime or not, because again, this TF-Lite GPU delegate is very generic. So if you are getting, let's say, 10% improvement on one device, then you will get almost the same performance on other devices. So in this case, optimization is very straightforward. And the same evaluation, the same strategy was used for final evaluation of solutions. So here you can see the results obtained in this challenge, and a couple of teams demonstrated exceptionally good performance, both numerical and runtime results. So the winner of this challenge is Team TLG, and as you can see, this solution is able to denoise Full HD resolution image under 40 milliseconds on target GPUs. So this is extremely low runtime, and if you try to process larger resolution images, for instance, if you want to process 8 or 12 megapixel images, you'll still get runtime less than 1 second, which is more than reasonable from a practical point of view. And this team also achieved the highest SSAM score and high PSNR result. At the same time, similar good fidelity scores were achieved by Team Hennis and Team Pag. The images reconstructed by these solutions also show exceptionally good visual quality. The solutions are slightly slower, but the results demonstrated by these models are still very reasonable. And let's see what are the solutions proposed by these teams. So here you can see the model proposed by Team TLG, and the architecture of the model is very straightforward. So as you can see, sometimes old tools or old ideas might be the best ones to use. So the guys used only convolutions and only skip connections. But as you can see, lots of skip connections and lots of convolutions. And so the overall architecture is basically a unit-based model, and it contains lots of skip connections, lots of both inside the blocks and additional residual connection from the input to the output of the model. And again, all these things together with proper training allow this team to achieve very good reconstruction quality and at the same time very good runtime, because the model does not contain anything except for convolutions. So in this case, it's compatible with any NPU, and its execution is extremely efficient. So yeah, this is a solution from Team TLG. So solutions from Team Phoenix, you can see it on the slide. It's much more complicated and much more interested from architectural point of view. So you will see the detailed description of this model in the next presentation. And for TPEG, you will also see a description of their architecture in the following presentation. So if there are no questions, then we move directly to the presentation from Team Phoenix. I think the author is here. So now we should have a presentation fast shade, fast self-augmented hierarchical asymmetric denoising for efficient inference. Do we have?
Yeah, so I'm going to share the screen now for
Yes.
the presenter.
Uh-huh.
Let me just see how I can do that.
Uh-huh.
Yeah, this should be fine, I suppose. Yeah, like that, or you should probably be able to.
Yes, we can see. Uh-huh.
Yeah, let me just do it another way so that I can
Uh-huh.
put it here so that we can also the audience can see it in
Uh-huh.
the proper way. One moment, please. Yes, good. I believe you should be able to see it.
Yes, we can see it.
Okay, the floor is yours. You might have to look at it, but try that. Maybe.
Hello, everyone. Thank you. Today I'm going to present our solution FastShade, which is essentially an extension or continuation of our work used as entry to this challenge. As it was already mentioned today, when we are designing neural network architecture for mobile devices, there are many challenges and differences from conventional architectures we have, for example, for GPUs for servers. There are many reasons for that, including power limitation, computational limitation, but most importantly, it's all about different memory topologies. So we have to think about efficiency of different operations in terms of I/O bottlenecks and so on. One simple example could be that if we are designing architecture for just a standard GPU, we can add one-by-one convolution for projection from one layer to another without hesitation. But if we are considering such operation on mobile devices, it can result in significant slowdown of inference. So we need to be very cautious about particular layers we are using in our architecture. While designing the solution, our key hypothesis and idea to verify was that we thought that actually denoising consists of two subtasks. One is structure preservation, essentially extracting edges and preserving them in final image. And another one is actually noise suppression. The first one is more global task, as it requires a larger context window to extract proper edges and context of our image, while noise suppression is much more local. And in our solution, we try to verify this hypothesis. And also we introduced several tricks which helped us to improve our final results. So as our architectural overview, it's based on UNet style network, which operates on two downscaled resolutions of original image. For downscaling, we used trainable 2x2 convolution with straight 2. For upscaling, it was standard pixel shuffle layer. And main computations performed by AFDB, stands for asymmetrical frequency denoising blocks. It's the blocks utilizing our idea with different processings of two different subtasks I mentioned. And another novel block is spatially gated upsampler we used for fusing skip connection features with upsampled features from our bottleneck. As the main convolutional layer, we used multi-branch parameterized layer, which is well demonstrated efficiency on mobile devices. Essentially, during training, it consists of multiple types of convolutions, and all of them can be fused in just single 3x3 or 5x5 convolution on inference, making it very efficient while demonstrating much better performance than just vanilla 2D convolution trained from scratch originally. So here it's our AFDB block. Essentially, the main novelty here is that instead of processing everything with just single convolutional kernel, we are splitting our channels. And what is interesting is that our experiments demonstrated that it's not necessary to have equal split like it's done in splitter-net architecture, which demonstrates also quite good results on this task. We observed that for low frequency features such as contours and edges preservation, it's enough to use just quarter of all features we have for this block, while for noise suppression, it's important to have more channels, particularly 3/4 of all features. Particular split was optimized by parameter search and so on. And after the split and processing with corresponding kernels, final results are concatenated back and processed with yet another convolution. And of course, we have residual connection allowing more stable training. And here it's probably most interesting empirical results we have. Essentially, we don't have in our training any type of auxiliary losses for explicit separation of domains, but so we are not forcing our network to train low frequency or high frequency features individually for those two passes we have in IFTB blocks. However, those results demonstrate that this separation happens internally during the model training by itself, induced by differences in branches. And one with 5x5 convolution obviously have much bigger receptive field. And here in the results of Fourier transform of the features, we see substantial differences in observed magnitudes. Particularly, what we've done here was we averaged all the features we have for validations part of this data set used in this challenge on our trained model. And we can see that in low frequency range, we observe reduction of magnitude from low frequency to high frequency, meaning that low frequency are dominated in low frequency range with 5x5 convolution. While for 3x3 branch, we see that response is more uniform, meaning it's just response to noise suppression across all frequencies. As for spatially gated upsampler, it's used for fusing our skip connection features with our outputs of FDB blocks. And here, the main challenge from classical UNet style models is that usually continuation is used, meaning that number of channels are essentially doubled after a skip connection, which is not efficient for mobile inference. So here we come up with a solution which includes also spatially gated mask acting as a local spatial attention. This mask is produced on our low resolution features, which are upsampled by nearest upsampling, followed by depth-wise convolution. In our ablation study, we demonstrate that such approach is more efficient than having other upsampling techniques, such as using transpose convolution for masks creation and so on. And also we demonstrated that such mask is beneficial for overall PSNR and SIM values. One small trick we used to improve our ultimate result was on image augmentation. Essentially, quite often in such tasks, it's very important to have a way which allows to expand available data set to improve robustness of the approach and its generalization and so on. And denoising task is quite special because image noise is localized. I mean, it correlates with image content, not just global camera settings or global image content, but also with very local features. And that's why we propose such simple but rather efficient approach. Given we have pairs of images, noisy image and denoised image, for training, we extracted noise residuals, applied spatial spatial shifts of residuals, and reapplied them to the noise image, creating artificially noised images while preserving local local features of the noise. And it was demonstrated in our ablation that such an approach is much more efficient than just applying Gaussian noising or other standard techniques for adding artificial noise. So to the results, as I mentioned, we have a parameterization of our model. So we trained not one model, but rather series of models with different number of channels as well as number of FDB blocks. And here's the results. As you can see, M version of the model provides the best balance between visual fidelity and quality of reconstruction while being under 50 milliseconds processing time, while bigger models allowing us to achieve essentially, to the best of our knowledge, state-of-the-art results on both PSNR and SSIM metrics, essentially expanding Pareto frontier on this data set. So yeah, that's our results. Thank you for your attention. And yeah, if you have any questions, and also feel free to connect if you like.
Thank you, Nikolai, for presenting your work. Do you have any questions? Okay, so if there are no questions, then we're moving to the next presentation. Sorry, do you have a question or? Okay, probably no. Yeah. Then the next presentation is real image denoising with knowledge distillation for high performance mobile NPUs.
Am I audible?
Yes,
you hear me?
Yes, we can hear you.
Okay. Okay, so hello everyone, and thanks for being here. I am Faraz Kiani, presenting on behalf of our team. My co-authors are Samad Kiani and Asad Ahmad, along with Professor Dr. Radu Timofte and Dr. Dmitry Ignatov from the Computer Vision Lab at the University of Würzburg. What we are presenting is real image denoising with knowledge distillation for high-performance mobile NPUs, our submission to the Mobile AI 2026 Challenge. The headline numbers are on the screen and we'll walk through all of them. But the one to keep in mind for the next 15 minutes is one on the right. On the same exported model, the dedicated NPU runs almost 4 times faster than the integrated mobile GPU. That finding, what we call the inference inversion, is what we think makes this work more interesting beyond the challenge itself. We will get to it near the end. Okay, so let's start with the problem. Every photo your phone takes goes through a denoising step. Deep networks have made that step dramatically better on desktop GPUs over the last few years. But there's a real and stubborn gap between what works in the paper and what actually runs on a phone. Three things that define the gap. Mobile NPUs support only a small set of operators natively. They have very tight on-chip memory tiles, so your activations have to physically fit inside SRAM at high resolution. And the whole system has to stay within a thermal budget. You cannot ship a model that throttles after 30 seconds of use. The table on the right makes this concrete. Self-attention, deformable convolutions, different convolutions, GLU, Swish, these all are centered on desktop, all problematic or unsupported on mobile NPU. The green column at the bottom, standard 3x3 convolutions, ReLU activations, nearest neighbor upsampling, that's the small set of primitives that every flagship NPU runs without falling back to slower paths. The green column is essentially the entire vocabulary our deployable model is allowed to use. A natural question at this point would be, why not just use the mobile GPU? It supports more operators. It's a known target. CPU we can rule out quickly. It's too slow, too power hungry. The mobile GPU is the traditional choice. Good FP16 throughput handles complex operators, but it draws a lot of power under load and it's shared with whatever else is using the display. The NPU is the dedicated AI accelerator, best performance per watt by a wide margin, tiled SRAM with very low latency. The catch is the one we just saw, a strict operator subset. And the moment you hit anything outside that subset, you fall back and your latency falls off a cliff. So our thesis, and this is the line in the column at the bottom, is design for the NPU first. Don't take a desktop architecture and try to make it fit afterwards. Constrain the architecture from the very beginning. Resolution quality, we can argue, can be recovered through distillation, and the rest of the talk is essentially the evidence for that claim. That thesis was put to test in the Mobile AI 2026 Image Denoising Challenge, which is the workshop this talk is part of. The setup was it was 650 paired noisy and clean training images plus 50 image validation set, all real noise from real smartphone sensors at full 8 megapixel resolution. Models are benchmarked directly on flagship handsets, the MediaTek Dimensity 9500 and the Qualcomm Snapdragon 8 Elite. Latency is measured in FP16 at full HD, and the official ranking combines PSNR and average runtime. Our result is on the right, 37.5 with dB held out test PSNR, and importantly, valid runtime on both flagship NPUs. We will show in a few slides why that end matters. Several strong submissions failed to produce a valid runtime on one or both target devices. Before getting into how the model actually works, here's the 4-bullet version of what we are claiming. One is an NPU-aware teacher-student approach, where the hardware constraints are baked into the student's design from the start, not added afterwards. The second is the student is built entirely from NPU native primitives, which mean stable, fallback-free execution on both target chips. The third one is the combination of high alpha distillation and progressive context expansion. Less a 1.96 per million parameter student recovers 99.8 parameters of a much larger teacher's quality. The validation PSNR gap drops to 1.63 down to 0.05 dB, 500th of a decibel. And the fourth one is the strong on-device runtimes, 34 milliseconds on the Dimensity 9500 and 46 milliseconds on the Snapdragon 8 Elite, both under the official Full HD protocol. Let's now walk through how we built this. This is the whole training and deployment pipeline on a single slide. We will only spend a few moments on it, and we will unpack each piece in turn. Top half is training. The noisy input goes into both a frozen high-capacity teacher and a lightweight student we actually want to deploy. Three losses combined: a ground truth MSC between the student and the clean image, a distillation loss between the student and the teacher's prediction, and an N1 loss on the ground truth. They combine with weights 100, 900, and 50. Those weight matters, and we'll come back to why. Bottom half is the deployment. We only export the student. AI torch converts PyTorch to TensorFlow Lite. The result is a 7.5 megabyte TF-Lite model that runs on the NPU delegate on both target chips. That's the whole picture. Now let's zoom in on each part. The teacher is what we use to define how good a denoiser can be on this data. It's a quality ceiling, but never a deployment target. It's a 3-level encoder bottleneck decoder unit scaling from 64 to 512 channels. Each stage uses a denoising block, 4 3x3 convolutions with dense internal aggregation, PRELU activation, a local residual. Skip connections concatenate encoder feature into the matching decoder stage. Downsampling is strategic convolution and upsampling is transport convolution. It has 41.6 million parameters in total, hits 37.71 dB PSNR on validation set, the highest we ever achieved during development. So we have a strong reference. But when we tried to deploy it on the NPU, it ran out of memory at full 8 megapixel resolution. Its intermediate activations are simply too wide for the SRAM tiling on the target devices. So this network defines the upper bound of the quality, but it can never be the thing that we ship. This is the student, the thing we actually deploy on the mobile phone. Same unit family, but everything is sized and chosen for the NPU. 16 base channels growing to 256 channels, 4 downsampling stages, and it has 1.96 million parameters in total. There are 3 design principles that drive this. Number one is we picked 16 base channel because that aligns with the SIMD widths of these mobile accelerators. Smaller widths leave the SIMD lanes underutilized. Wider widths spill the activation tiles out of on-chip memory. The second is only NPU-friendly operators, standard 3x3 convolutions and ReLU activations, no GLU, no switch, no attention modules. Anything that historically framework fallbacks is gone. The third one, and it is the crucial one, and this is one of the design decisions that produces the inference emergent finding later. We replaced transpose convolution in the decoder with nearest neighbor upsampling followed by a 3x3 convolution. Transport convolutions do zero insertion logics internally. And that logic is exactly where less flexible NPU drivers fall back to the CPU. Nearest neighbor plus a convolution has the same expressive power and they run entirely on the fast path. This is only the building block inside the student, and it's repeated identically across every encoder, decoder, and the bottleneck stage. There are 3 things to notice here. The first one is the channel reduction bottleneck, F to F over 2 and back. This cuts MAC count substantially, and a residual skip preserves the full capacity. The second is the operator palette is deliberately minimal, convolution 3x3 plus ReLU, that's it. And the third one is the identity residual. The local skip stabilizes training and keeps low frequency content flowing through the block unmodified. So the block only has to learn the correction. That's the entire building block, one small block used everywhere. It's deliberately boring component, and boring is exactly what you want when boring means it never falls off the NPU fastpath. Now, how do we train this small student to behave like the huge teacher? This is the distillation objective. The total loss has three components, weighted 100, 900, and 50. The middle one is the distillation loss, and it is the dominant term by far. And that's what we mean by high alpha. Alpha is the relative weight on the distillation term versus the ground truth term. And at 900 to 100, alpha equals 0.9. Walking left to right, the ground truth MSE is the standard reconstruction loss against the clean image. The distillation loss is the squared error distance between the student's prediction and the teacher's prediction. And the Altman penalty against the ground truth sharpens the edges and stabilizes the high frequency texture. Here's the subtle but important point at the bottom. With alpha at 0.9, the teacher's clean prediction dominates over the noisy ground truth. And the reason that matters is that even the clean ground truth image is real denoising datasets still contain residual sensor noise. If you train the student aggressively against those, it learns to reproduce that residual noise because the loss can't tell noise from real content. By making the teacher's noise-free output the primary supervision signal, the student inherits a cleaner restoration manifold than the dataset itself provides. That insight, more than anything else, is what closes the quality gap between the 1.96 million parameter model and 41 million parameter one. Two final methodology pieces before we get to results. On the left-hand side, progressive content expansion. A lightweight network with only 16 base channels has a restricted receptive field. It cannot learn about the large-scale structure if you only train it on 256 by 256 crops. So we grow the crops in stages. We pre-trained at 256, mid-stage fine-tune at 512, and final fine-tune all the way out to 1024 by 1024 pixels. Exposing the student to that much spatial context lets it learn the global luminance gradients and structural coherence that are mathematically invisible at smaller crop sizes. And on the right-hand side, the export pipeline, PyTorch model in NCHW format. HTorch wraps it with a layout fuse permutation step because the mobile NPU wants NSWC for the maximum contagious memory released during special convolutions. The result here is a 7.5 megabyte FP16 TF Lite model that targets the NPU delegate. One detail that matters, we ran a numerical parity check between the PyTorch reference and the exported TF Lite, and the max deviation was less than 10 to the power minus 4. So the export is faithful and there is no quality drift introduced at the conversion. All right, so that's the method. Now, does it actually work? So this is a experimental protocol. These are the details, not findings, but they matter for the reproducibility. The data set used in this challenge was provided by the challenge organizers. It has 650 training pairs, 50 validation pairs, plus the held out test set. We extract 256 by 256 crops with a 2 pixel buffer to avoid the edge bias, and plus standard flips and 90-degree rotations. And the training setup used in this challenge was the PyTorch 2.4 on a single RTX 4090, Adam with cosine annealing, gradient clipping at 0.1, alpha at 0.9. It was trained for 200 epochs retraining, then 20-30 epochs of fine-tuning at the larger crop sizes. The evaluation criteria was PSNR and SSIM on RGB channels with a 1 pixel boundary crop computed at the full 2432 by 3200 resolution. And the on-device profiling was done on Physical Dimensity 9500 and Snapdragon 8 Elite handsets, FP16 at Full HD using the official AI benchmark application exactly as the challenge requires. And this is probably the most informative table in the paper. 5 architectural stages, not a clean ablation in the traditional sense, but a boundary seeking progression that maps out where the quality meets on-device viability. So the stage 1 is an attention augmented design, small at 340K parameters with spatial and channel attention. 31.68 dB PSNR, it looked promising on paper but failed to compile at a high resolution because of the attention operators. Stage 2 is the high capacity teacher we showed you earlier. It has 37.71 dB PSNR, the best quality we ever achieved, but out of memory on the NPU at 8 megapixel. Raw capacity is not enough if it violates device level memory constraints. Stage 3 was an aggressively efficient 12-base filter. Only 22 milliseconds, runs fine, but 34.86 Gbps, too narrow to recover the fine textures. Visible oversmoothing was there in the outputs. Stage 4 was to widen the stage 3 to 16 filters. It has 1.96 million parameters. Same architecture as our final model, but trained without distillation. It got 36.08 dBPSNR at 46 milliseconds. It was stable on the NPU, but still 1.63 dB behind the teacher. So the stage 5, it's the same architecture as the stage 4, but now distilled from the 41 million parameter teacher. 37.66 dB PSNR, same 46 millisecond latency because the architecture is unchanged. Now look at the gap between stage 4 and stage 5. It's the same model, same parameters, same latency, same memory footprint. The only difference is the supervision signal. Distillation closes the 1.58 dB of the 1.63 dB PSNR gap. That's the cleanest piece of evidence in the paper. Raw capacity is not enough. Extreme efficiency is not enough. And what does close the gap is distilling teacher knowledge into NPU native primitives. Now the actual challenge results, the 4 numbers across the top are high-level summary, 37.58 dB test PSNR, 0.9098 SSIM, 1.96 million parameters, and it's 7.5 megabytes on disk. The leader board in the middle is sorted by held out test PSNR. 3 things that stand out. At first, we have the highest PSNR among the teams with valid runtimes on both target NPUs. Second, if you look at the column, if you look at the right column, the Dimensity NPU runtimes, several strong submissions failed to produce a valid Dimensity runtime at all. Some have stronger Snapdragon runtimes than ours, but they don't run on Dimensity. So the cross-platform NPU compatibility is genuine and binding constraint in this challenge. And the third one is our runtimes are competitive. 46 milliseconds on Snapdragon Elite, 34 milliseconds on Dimensity. Not the fastest in the field, but well into real-time territory on both. The point of this call out on the right is that the quality and cross-platform NPU compatibility are distinct objectives, and combining them is genuinely hard. Several stronger on-quality methods don't run on one of the 2 platforms. Several faster on-runtime methods give up too much PSNR. Our position is the best simultaneously strong point on the 2-dimensional trade-offs. One thing worth being upfront about the challenge is the official challenge ranking uses GPU runtimes, not NPU runtimes in the scoring formula. So on GPU, we are not the fastest. We are transparent about that in the paper. What we are arguing is not that we want the historical metric, but that metric is shifting towards NPU first evaluation, and that under the NPU oriented rescore, we are the strongest combined entry. This slide combines 2 things, the distillation result quantitatively and a qualitative example. Left side top is the PSNR gap collapse without distillation, 1.60 dB behind the teacher. And with high alpha distillation, it's 0.05 dB. That's 99.8% of the teacher's quality recovered into a model that's 21 times smaller. And on the left side bottom, the per image PSNR gap on the 50 validation images sorted from largest to smallest. Most points cluster near 0. Mean gap is 0.08 dB, and notice the negative values on the left. Those are images where the distilled student actually outperforms the teacher. Not the headline finding, but interesting. It suggests that the student is not just mimicking the teacher, it's learning a representation that occasionally generalizes better. On the right-hand side, we have a representative validation example from left to right. It's noisy input, our student's output, ground truth. Top row is the full image, bottom row is the zoomed out crop. The visible sensor noise is gone in the flat regions. Fine texture is preserved in the foliage and edges. And importantly, the output does not have that flat plastic look that every compact denoiser often produces. It reads as a natural photograph. And that is our most interesting empirical finding and the one we would like you to walk out of the room with. We exported one model that the student wants, and then we ran it on 3 different accelerators on the same hardware. The Snapdragon 8 Elite integrated GPU, the Snapdragon 8 Elite NPU, and the Dimensity 500 NPU. The left bar is the same model on the integrated mobile GPU. It has 132 milliseconds. The middle bar is the same model on the Snapdragon Elite NPU, 46 milliseconds, 2.86 times faster than the GPU. And the right bar is the same model on Dimensity 9500 NPU, 34 milliseconds, 3.88 times faster than the GPU. The conventional wisdom for low language vision on mobile has been that the GPU is the primary acceleration path, and NPUs are for simpler inference workloads. What we are seeing here is the opposite. When you design a model so that every operator lives on the NPU fast path, no fallback everywhere. The no fallback anywhere. The dedicated accelerator beats the general purpose mobile GPU by a wide margin. We think this is going to be increasingly true for the next generation of mobile imaging. Operator compatibility and accelerator native architectural design are becoming primary determinants of the runtime, not the secondary implementation details. So to bring it all together, we presented an NPU-aware teacher-student approach for real image denoising on flagship mobile hardware, and there are 3 takeaways. One is NPU first design, constraining the student to NPU native primitives from the very start produces a stable, fallback-free execution on both flagship SoCs. The second is high alpha distillation works. A 1.96 million parameter student recovers 99.8% of a 41 million parameter teacher's quality. The validation gap drops from 1.63 dB to 0.05 dB. And the third one is the inference inversion. When the architecture genuinely matches the accelerator's fast path, the NPU is up to 3.88 times faster than the mobile GPU on the same exported model. And so the dedicated AI accelerators are not a constrained alternative anymore. They are the preferred deployment target. The model and its training statistics are released through the Lemur NN dataset at the URL on the right. And that's my time. Thank you. And we'd love to take any question if you have any.
Thank you for the presentation. So do we have any questions? Okay, I guess no. Then we are moving to the next challenge, to RGB image enhancement challenge. Okay, so we're now done with image denoising, and now we move here to generic RGB photo enhancement problem. And the idea of this problem is also quite easy, that the majority of photos taken with mobile devices, they are not of sufficiently good quality. And what is more important is that we also have lots of photos taken with older devices, taken years ago, with older smartphones, with older cameras, and the quality of these photos is also not good. And of course, we want to improve the quality of these photos. And in the previous challenges, we were looking at one particular aspect. In super resolution challenge, it was just the resolution. In the denoising, it was just removing noise. This problem is considerably more trickier, because in this case, we need to improve all aspects altogether. So we need to improve resolution, we need to improve noise, we need to improve colors, we need to remove artifacts. So We need to add details, improve texture. So in this case, it's more considerably more comprehensive problem and much more challenging. And the participants, were proposed to solve this task to improve low quality smartphone photos. And they had to design efficient solutions that would be executed on mobile GPUs and been able to process full HD photo at reasonable time. For the dataset, we used deeper dataset, and this dataset contains a number of different input smartphones, a number of source smartphones, and in this case, we use the most challenging setup. So input photos were taken with iPhone 3GS camera that has 3.15 megapixel camera sensor, and these photos are of extremely poor quality. And the target photos were captured with Canon 70D DSLR camera. So in total, there are over 5,000 image pairs and around 160K image crops. And again, the goal for the participants was to design solutions that would improve old iPhone photos as much as possible. In this competition, we use 3 metrics. So the one is the standard fidelity score measured by PSMS SAM. But unfortunately, the scores are not always reflecting the real quality of reconstructed images. So in this case, we additionally used mean opinion scores measured by photographers where they had to evaluate the quality of reconstructed photos. And the runtime of the models was, as in the previous competitions, measured on Snapdragon 8 Elite Gen 5 and MediaTek Dimensity 9500 SoCs on their GPUs. So the final score, it was composed of both mean opinion score, PSNR score, and runtime. Again, for validated runtime of solution, the participants used a benchmark to track the progress locally, and the same setup was used for the final evaluation. Here you can see the results of all valid submissions obtained in this competition. And here we have one very clear challenge winner. This is team Dahua IAG. So basically, the solution proposed by this team excelled in all metrics. It achieved the best PSNR, SSM scores, the best mean opinion score, like far better than all other solutions, and at the same time, the best runtime results on these GPUs. And moreover, the solution is also compatible with NPUs, with NPU of Snapdragon 8 and Gen 5. The model proposed by this team was able to process one full HD resolution image under 40 milliseconds on mobile device. Again, this means that you can also apply this model for processing full resolution images. Okay, in case of iPhone, this full resolution image is not very different in terms of size from full HD image, but if you're training this model to process, let's say, 8 megapixel or 12 megapixel photos, you can still run this model on the mobile GPUs, and it will be able to process these photos under 1 second. The second best result was achieved by Team Capybara, and in their case, the results were also the model was also reasonably fast and demonstrated sufficiently good visual quality. So let's look at the solution from the winners. So here you can see the overall architecture of the proposed model. But the key idea was not in the architecture. The key idea was in using teacher model, in using transformer-based architecture for as a teacher, as a teacher network. And this architecture was trained on this dataset and was able to achieve very good reconstruction quality. And then this model was used to generate synthetic ground truth, to generate ground truth images for inputs from deeper dataset. And the idea behind this was that in the deeper dataset, input and target images, they are aligned, but sometimes there is a few pixel mismatch between input and target, because these images come from very different sources. So imagine that one image was captured by 3 megapixel iPhone sensor and another by 18 megapixel DSLR. So you can expect that there would be mismatch even if you are trying to align this image as well. So to avoid this mismatch, the guys first trained Regenex Former on the entire dataset and then generated target images, the target images not presented in this dataset, but that would be used by smaller student model, and then trained the student model on this generated on this augmented dataset. And in this case, for student model, there was no need to deal with misalignment because images produced by Rogenix formula, of course, they were aligned. They were perfectly aligned. And yeah, all in all, this approach allowed this team to achieve much better reconstruction quality while using a quite shallow network architecture. And for this network architecture for student models, they used a modified version of PLUnet, which architecture you can see on the slides. And the model was trained with a combination of multi-scale L2, MSN, and perceptual losses. The second team, runner-up is Team Capybara. You can see their architecture on this slide, and we'll have a presentation from the guys. So they will tell you more about their solution and about particularities, about training, and about architecture. So if there are no questions, then we are moving to their presentation. Other authors here.
Oh, yes, I'm here.
Thank you. So you can start your presentation.
Um, so can you see the screen?
Yes, we can see the screen.
Okay. So hello everyone. My name is Tohandak, and I will present the paper titled Bridging the Training Deployment Gap, Gated Encoding and Multi-Scale Refinement for Efficient Quantization-Aware Image Enhancement. So first off, the motivation. When we train a model, we tend to train it using full precision or like FP60. But when deployed to the user's phones, they will have less memory than we have. And so we have to quantize it. But the quantization model will suffer from the precision loss. And you can see in the image, the FP at the full precision, we have a larger range of value than the integer, and multiple points in the full precision range can map into a single point in the integer range. So as you can see in the image, in the right, in the below image, the integer, the quantized results is blurry, and you can see the number like in the full precision results. And secondly, the quantized results will suffer from color shift and texture distortions. The as you can see in the image, the wall is greener compared to the result from the full precision models, and the sky is also pinker, which indicates the color shift. So we came to two contributions. First is our proposed model, and second is the quantization aware training. So the model can adapt to the quantization error. So our model looks like this, and it follows the unit architecture. And we have two main components, that is gated encoder block and the multi-scale refinement. About the gated encoder block, the dual branch architectures will extract the features and apply the nonlinear element-wise gating mechanism. And you can imagine the gating here as a attention mechanism when we do a element-wise product between the two feature. The second feature can act as a attention mechanism that will suppress or boost the signals from the first features. Next is the multi-scale refinement. It is a simple block of convolution 2D, instant normalization in Leaky Relu. And given the input feature F, the block will apply some convolution 2D, instant normalization in Leaky Relu, and then concatenate it with a skip connection that will follow by a one-by-one convolution 2D. And they will all go through a group of convolution and activation layers before merging with another skip connection. And this refinement block is used to refine the features in both the encoder and the decoder block. And this is to preserve the global illumination and the local texture from the feature maps. Next is the quantization. And in the forward pass, we will have some frequent nodes, and they will simulate the quantization error for the model to learn to adapt to it. And when the model finishes calculating the loss, the gradient will propagate back with the straight-through estimator, STE, because the routing operation in FAC1 nodes are not differentiable. And when deploying, we just need to convert the model weights to integer and we can have the result model. So a bit about training. We use NVIDIA RTX 8000, A6000 with 48 GB VRAM, and we use BSNR loss, the cosine similarity loss, and outlier loss, and we do some ablation, and we try to replace the cosine similarity with the multi-scale structural similarity, like the previous winner, the previous year top 1 winner. And we see that the training took longer, the structural similarity score does increase, but the BSNR is lower than compared to our loss. And our loss also have a lower training time. About some results. First, the quantitative results. Here is the table of the submission type of my, and we exclude some teams. So as you can see, our method is comparable to the top 1 team, and despite that the inference time is higher, we still manage to get the model high performance. And to compare the full precision and the quantized version, we have this table. The quantized version reduce the inference time of from 469 milliseconds to 19 milliseconds. And with the quantum neural network hexagon tensor processor, we reduce the model inference time from just 151 to 41.4.8 milliseconds, which is reduced by 72%. The quantization aware training does help the model recover 0.474 dB in the BCSNR and about 0.111 in the SSIM. And we also do some ablation studies on the model architecture and the channel of the model. And we found that the resolution refiner, which is the multi-scale refinement at the encoder blocks, actually contribute the most to the model performance. And removing it will cause the PSNR to deteriorate significantly. And about the channel, we find that the C equal 24, we have the best trade-off, the optimal point between performance and the inference time. But we choose the 32 because we try to get the testing results looks better. And for the qualitative results, as you can see in the right blocks of image, the quantized model without the quantization aware training, we cannot see the numbers inside the license plate, but for the quantization aware, with the quantization aware training, we can see that the model can recover some of the number in here compared to the full precision. And we also compare to the baseline from the dataset paper and also the PPCN paper. Thanks for listening.
Thank you for the presentation. So do we have questions? Okay, seems like no. And then we are moving to the next challenge.
Okay, thank you.
Thank you for presenting this. So we're moving to the long smartphone ISP challenge. So in the previous task, we had to improve photos that have already been captured. And yeah, that was captured maybe years ago or were captured right now by the ISP system of the phone and want to improve different aspects of their code. But we can go deeper and we can try to improve the photos, the original raw photos. So the photos that haven't undergone processing by ISP. And this makes a lot of sense for a couple of reasons. For instance, raw photos captured by smartphones, they contain much richer information. So these are typically 12-bit to 16-bit photos. And of course, after processing, you are losing lots of this information and you are getting 8-bit photo. In this case, it makes sense to try to utilize this deeper, richer information, and at the same time, we would like to replace the entire classical ISP system in smartphones with a single deployment model that will take into account all processing, all enhancement needed for achieving good RGB image, and will again completely replace the ISP system in your mobile camera. And the participants this time were proposed to solve this problem, and they had to achieve to design models that can achieve good performance on mobile GPUs. And here the target was to achieve good runtime when processing 5 megapixel photos from mobile devices. For the dataset, the participants were proposed to use Fujifilm Ultra SP dataset that contains pairs of photos captured with Sony Exmor sensor that was used as our source camera. And high quality photos were captured with a medium format Fujifilm GFX 100 camera that contains 102 megapixel sensor and that produces quality that produces photos of extremely good quality. So it's really difficult to find any flaws in the photos captured with Fujifilm, so they served as a perfect ground truth for in this dataset. And again, the participants had to transform original raw photos in the left column. You can see visualized raw photos into something that looks like this. And you can also, on this figure, you can see the difference between smartphone ISP and the photos obtained with Fujifilm camera. So there are huge differences in small details, in color rendition, in pretty much all aspects. And performance here was located using the same metrics as in the previous competition. Again, it's fidelity scores measured by PSNI SSAM, mini opinion scores for checking the actual quality of the reconstructed RGB photos, and the runtime that was evaluated on the same SoCs on the same mobile GPUs. And the final score combined both visual, numerical, and runtime results. And again, for checking the performance of the models, the participants used a benchmark application to check the runtime of the local devices. Here you can see the results obtained in this challenge. Our winner is Team Mialgo. They were able to get best PSNI SSAM scores, very good mean opinion scores, and again, the fastest runtime. They were able to reconstruct one 5 megapixel RGB photo on both GPUs under 30 milliseconds. And these results, again, extremely great because this means that with this model, you can process easily 12 megapixel photo and do it under 1 second. And this means that you can just deploy this model in practice, especially if you're working with different kinds of mobile cameras present in various ISP boards, various IoT boards, because these cameras usually lack a proper ISP system at all. So images reconstructed with cameras present in IoT devices, they usually deliver very poor image quality. And with such models, you can run them efficiently even on GPUs and get much better reconstruction results than with any default ISP. And additionally, a solution from Mialgo is able to run on NPUs, demonstrating quite a good speed up on the Dimensity 9500 NPU. And by the way, here you can also see that the actual speed up on NPU really depends on the architecture you use. For instance, in the previous competitions, we usually saw that much better results were achieved on Snapdragon 8 Elite Gen 5 NPU, so compared to GPU-based execution. Here we have vice versa situation. So for NPU in Snapdragon SoC, we get 3 times larger runtime than on Snapdragon's GPU, but for Dimensity chipset, it's vice versa. For NPU, we're getting 2.5 times speed up compared to GPU-based runtime. So again, the model, the operators that you're using, even their order might significantly alter the speed, the runtime of the model on different platforms. And again, the exact runtime depends on NPU design. So it's all about the compatibility of your architecture with each specific NPU. And quite often you cannot understand this compatibility without trying and without optimizing the model for this endpoint. So all theoretical ideas, they may not work in practice. And yeah, the runner-up in this challenge is team AVC2. The model from this team demonstrated almost the same visual and numerical results, but it is slightly slower than the solution from team Mialgo. So let's look at the architectures from the winners. So here you can see LKS-NET model proposed by team Mialgo. It is based on SciNet architecture. And yeah, so overall it's quite simplistic model. There are not so many layers in this architecture, and this is the reason why it is so efficient from a computational point of view. But yeah, there are still a couple of important blocks. So for instance, you can see here channel attention, and in this computation, for this task, channel attention is extremely important because it is usually responsible for white balancing, for color correction. Without channel attention, you won't be able to achieve good results because just pure convolutions, they usually unable to do proper white balancing because it depends on the overall content of the image. And the same refers to color correction. So, and channel attention, it's very simple, it's very cheap operation. So here, for instance, it's just average pooling plus 1 times 1 convolution plus point activation. That's it. But it gives you much better results for problems where you need to make global image adjustments. And yeah, there are also quite a number of there are skip connections. Again, as always, they are very important if you are trying to enhance images. And yeah, so apart from that, the model contains only pixel shuffle, convolutions, yeah, one depth-wise convolution and a few activations. But nevertheless, this model was able to achieve quite good results. And it was trained with few losses, with color loss from the DPIP paper, with LPIPs, with SSAM, and with Gonzalez similarity loss. Now we're moving to the second team, AVC2, that achieved the same numerical and visual results. In this case, the architecture is a little bit different. We can still see almost same channel attention block here, but yeah, it's a little bit different. The key idea here is also using reparametrization. So in this case, the authors use multiple convolutions during training, and they also used batch normalization after these convolutions. And during the inference, all these convolutions and batch norms, they fused into one convolution because you no longer need batch norm. And the same goes for this block. So this allowed the authors to get quite efficient and quite small model while getting good numerical and visual results. And the model was trained to minimize a one-loss function. So you can find again the details of these solutions and other solutions in the challenge report. Do we have any questions here for this competition? Okay, good. So if there are no questions, then we're moving to the last challenge presentation. One moment. Which is bokeh effect rendering. So bokeh effect, I think it's also familiar for everyone. So this is just artistic effect that consists in blurring out of focus regions and making the main object still shown. And for mobile devices, generating this bokeh effect is unattainable unless mobile device has a huge camera sensors. There are a couple of smartphones with 1-inch cameras, but yeah, if we are talking about normal normal sensor size, and yeah, it's very difficult to get pronounced and beautiful bokeh effect on the resulting photos. And therefore, such effects are usually rendered computation. And this problem is actually probably the hardest among all considered tasks, because in all previous competitions, it was enough to work with local regions of the image. You don't need to have huge receptive fields because almost all problems, okay, super resolution, you don't need even to know about the contents on the image. The noise is same. Image enhancement, yeah, in this case, you need to know some global parameters to adjust brightness, to fix colors, but still, you don't need to know everything. And here, in case of bokeh effect, you really need to understand semantics of the image because you need to blur everything except for the main object. And in this case, you need to process the entire image and to understand what is the main object, where are its boundaries, and what regions should be blurred. Because of this, yeah, this is much harder problem that requires understanding of the entire image. And yeah, the participants were proposed to solve this task. Again, they had to design models that would run fast on mobile GPUs and process 1000 times 1000 pixel images. And this is a resolution that is typical for the majority of photos published online, especially in Instagram or in other media services where people usually using such tools to blur background and to make their photos or photos of some objects looking nice. For training the models, the participants used EBB dataset that contains 5,000 image pairs captured with shallow and wide depth of field, shallow and wide aperture. And in this case, this resulted in shallow and wide depth of field images. So image pair one image contains blurred background, and the second is sharp. And using these images, the participants have to train their models and come up with some solutions that can also mimic this bokeh effect and at the same time be efficient, run efficiently on smartphones. In this competition, the main metric was mean impedance score. For the final evaluation, PSNR same scores were not used because it was shown that these metrics are completely irrelevant for this task. So we can get a solution that shows top PSNR same results, but the image can be completely corrupted and it would be extremely bad or extremely bad quality. And vice versa, your image might exhibit very nice, very pronounced bokeh effect, but you'll be getting low PSNR same scores because of different mismatches caused by this blur. So in this case, for the target evaluation, we used mean impedance score as measurement of image quality and runtime for checking the actual speed of the model on mobile device. And as before, the participants used a benchmark application for checking and tracking the runtime of the models. And for the final evaluation, we use the same setup. Here you can see solutions proposed, valid solutions submitted for this competition. Again, the problem was very challenging and it was very difficult to come up with something that is computationally efficient and that produces nice results. But we had two teams that really succeeded. We have a team that XSweep, VIP, that designed extremely fast model. So the model proposed by this team, it takes less than 30 milliseconds to generate bokeh effect, and this effect is still of high quality. And yeah, even more, this model is also compatible with NPUs from Snapdragon and Dimensity SoCs, so you can run this model both on GPU and on NPU. And you can achieve very fast runtime and good reconstruction results. The best visual results were achieved by Team Modern AI Studio, and they were able to get top PSNR, SSA, no pips, and impedance score performance in terms of visual quality. Yeah, this solution was the best, and we'll see why. But yeah, the runtime of this model was much larger, so this architecture is considerably heavier. So let's look at the solutions. The first solution from the XVIP, it will be presented in the next talk. So the authors will tell you in detail what they designed and what are the ideas behind this architecture. We'll talk about the second solution from Team Modern AI Studio. And so why the guys were able to achieve so good reconstruction results? Because they use transform-based architecture. So they basically adapted transformer model and adapted it a little bit for this task. and used it for this problem. And as expected, they were able to get the best visual results, the best quality of bokeh among all solutions. And yeah, so the key, I would say, takeaway message from this work is that even if you are using transformer model, even if you're running it on large resolution images, because it's not like a very tiny image where you're doing some classification stuff. No, it's image to image mapping from 1000 pixels to 1000 pixel resolution. And even despite of this, even despite using a huge model with lots of transformer blocks, it was still possible to run this model on mobile device. Moreover, we can see that it took less than 2 seconds when running this model on Snapdragon 8 Elite and less than 3 seconds on Dimensity 9500 SoC. And why I'm pointing at these numbers? Because you can see on this slide Google Pixel 2 phone, and this was the first device that used computational photography to generate this bokeh. So it had a separate mode where you can just computationally produce bokeh, and there was a model running in the background and applying this effect to captured images. And this was one of the features of this phone. This algorithm was also described in the paper by Google. And yeah, the main point is that processing one photo on this device took around 5 seconds. So it was okay just to release a phone that takes a photo and then takes 5 seconds to process image in background and then release image with bokeh effect. So this means that actually what the solution proposed by team Moton AI Studio, you can also use it on commercial devices if you really need to have a very good image reconstruction. If your setup allows process an image in the background under 5 seconds. So if this is the case, then you can deploy this model and you can get good reconstruction results and better reconstruction results than any other method. Without using any extra data, without using depth information, without using dual pixel sensors, just reconstruct bokeh effect from one single image. So yeah, and the other aspects, that as you can expect from transformer architecture, it had a multi-head attention mechanism, and the model itself was trained to minimize combination of L1 and Fourier frequency domain losses. And yeah, this was the key to achieve top results in this competition. So right now, we move to the winner of this challenge, to team Detects VIP, and they will present in detail their solution that was extremely efficient. Can you start sharing? Okay.
Today,
Yeah.
it is my great honor to present to you one of our latest works, Light Bokeh, compact model for real-time bokeh rendering. This research comes from the State Key Laboratory of Mobile Network and Mobile Multimedia Technology, ZTE, China. We focus on achieving efficient, high-quality image processing on mobile devices and bokeh rendering is one of the key technologies in computational photography. We mainly introduce the following: introduction, challenge results, limitations and innovations, solution, visual comparison, conclusion. The MAI Realistic Bokeh Rendering Challenge focuses on developing a mobile AI model that achieves a high-quality DSLR-grade bokeh effect while running quickly on smartphones. Visually, the goal is to transform a sharp subject photo left into a realistically blurred background right, emulating high-end optics. Evaluation criteria include quality measured by mean opinion score, MOS, and speed measured by runtime on a target mobile platform. The organizers of the MAI 2026 Realistic Bokeh Challenge conducted a comprehensive evaluation of the results submitted by each participating team on the EBB test set. This evaluation employed established image quality metrics, including mean opinion score, MOS, peak signal-to-noise ratio, PSNR, and other relevant quantitative and perceptual metrics. To evaluate the model's efficiency, we measured its inference latency on a 1024 times 1536 times 3 resolution image using AI benchmark FP16 precision with TF-Lite GPU and NPU delegates. The tests were conducted on platforms equipped with MediaTek Dimensity 9500 and Snapdragon 8 Elite Gen 5 chipsets. The results are shown in Table 1. The final score is calculated by incorporating the average GPU inference latency from both test devices, the mean opinion score, MOS. Our TinyUNet strikes a good balance between performance and bokeh, resulting in a higher overall score that significantly surpasses the scores of other team submissions. To address the limitations of high per-frame latency and unintended foreground blurring under bokeh rendering, we introduced 3 key innovations. First, we propose Light Bokeh, a compact model specifically designed for real-time bokeh rendering, which significantly reduces computational overhead. Second, we employ depth-guided training with a spatially weighted loss to better preserve foreground details by leveraging depth information. Finally, we apply a lightweight post-processing step via a single residual block network that sharpens the foreground, effectively correcting any residual blur introduced by the bokeh effect. Together, these innovations enable efficient, high-quality bokeh rendering with crisp foregrounds and minimal latency. Two-phase architectural overview. The UNet-based architecture includes 4 residual blocks and replaces direct bilinear upsampling with a transposed convolution block to boost network performance. Additionally, an enhancement module is incorporated into this network to address the foreground blur issue. Depth maps generated by Deep Anything v2 are used for depth-guided training with a spatially weighted loss. A 2-phase training strategy was employed for the process using TensorFlow. In the first stage, we used the EBB dataset to train end-to-end bokeh rendering bi-randomly. cropping images into 1024 times 1024 pixel blocks as input. The batch size was set to 16, limited by memory. The training phase utilized a composite loss function comprising L1, loss, sim loss, and perceptual loss, and utilized the atom optimizer beta 1.0.9, beta 2.0, 999 with an initial learning rate of 1 times 10⁻⁴. A decaying learning rate scheduler was used, decaying every 120 epochs for a total of 600 epochs of training. In the second phase, to improve the end-to-end foreground blurring issue, we added an enhancement module to make the foreground clearer, using only one residual block. The training dataset for this augmentation model uses the ground truth GT data from the original image of EBB dataset. Degradation techniques such as blurring, adding noise, and reducing contrast were employed. Pairwise training sets were constructed and only L1 loss was used during training. We validated the effectiveness of our strategy. Training based on depth map-guided spatial loss calculation and adding an enhancement module significantly improved foreground texture detail preservation and sharpness. We compared our model with BGGAN and PyNet without considering computational efficiency. Our model is very fast, but has a significant advantage in foreground sharpness. Conclusion: our lightweight solution achieved first place in the 2026 Mobile AI Realistic Bokeh Rendering Challenge based on overall metrics. We propose a two-stage network. Training uses depth-weighted loss with no inference overhead, and inference adds only a residual block to sharpen the foreground. That's all for my presentation today. Thank you for listening.
Thanks for the presentation. Do we have any questions? Okay, so if there are no questions, then we have a short break. We have break till 1 p.m. So we have 35 minutes break, and see you all in 35 minutes.
So if anything happens, you can just take control of the
So I guess we can resume the workshop. So do we have our next presenter ready? So right now we have a talk accelerating on-device LM inference via activation guided FFN installation on Raspberry Pi. So do we have any presenter on site? People from Korea Electronics Technology Institute.
Wait a
Sorry, So you can or can't see them? So do we have presenters or we don't have them?
Sorry?
Yeah. You
So,
Yeah. I said 10.
sorry, I just don't see what's happening in the room and I can't hear you well. So in this case, yeah, I don't understand if we have guys getting prepared for giving a talk or we don't have anyone.
I'm talking what happened.
You can just connect this. Probably this as well. Andre, is it audible to you?
Yes, I can hear.
Yeah, okay. We just connected the speaker's laptop so that the audience can see the screen.
Okay, great. Yeah.
I think. How will you join in Zoom?
Yes. You need to join Zoom, so the presentation is recorded and.
You're joining the Zoom.
Mhm.
Oh, okay. Yes. Click live maybe over there on top.
Yeah, so there is some link, on the workshop webpage. Yes.
You cannot access. Okay.
So long.
Yeah, I don't know too. I'm also one of the speakers.
So have you managed to connect to Zoom? Okay, so I see you're probably connected.
Andre, is it okay? Is it all
Yes,
visible
yes,
and audible?
yes, we can see the screen. Yes, and we can hear you.
Really sorry for waiting.
Okay, great, perfect.
You see the presentation?
Yes, I can see the presentation.
Okay. Good afternoon, everyone. I'm Hunter from CATI. So this is title of the accelerating on device RNA inference via activation guided FFT distillation on Raspberry Pi. So this paper is related to efficient LLMs challenges on Raspberry Pi or mobile AI workshop. So before the describing our method is presentation is ICCB workshop of AI workshop, AIM. Let me show the baseline and the model, and in our framework, we evaluate the diverse models such as Llama 3.2 1 billion and QN3 0.6 billion. So in this case, the key finding is the model under integer 4 right alternative achieves the best challenge score all across all configuration. So in this case, we only consider the system level profiling. So we only choose the model file format such as PyTorch or LiteRT and the Llama or QN model. So first of all, this lecture, this paper extends directly on our prior work, CVPR workshop paper. Prior work performs the system level profiling to select the optimal model and run times such as PyTorch and LiteRT due to limited submission format of challenging. The first one is how we profile. Prior work conduct system level profiling, compare how small model efficiency. In contrast, based on the system level profiling, we got to decision the model
we extend the modular profiling. Profiling is include analyzing latents precisely into potential model and feedback network model, and others. Others include the weight input output cost. This final result is what revealed the bottleneck. The second one is the compression method. Prior work only applied the post-training computation, PTQ. In this paper, we propose the structural compression, what is expressed by feedback network distillation, which correlates to the intermediate dimension from half size. So in this way, we achieve a better challenge score. So this page shows our motivation in detail. Deploying LLMs on the Raspberry Pi is we have three considerations. First one is the hardware has several constraints. Every token generation of the code pages cycle running entirely on CPU. Based on our profiling, the code pages is more the dominant processing of LLM class. Second one is the PTQ alone is insufficient. Contention reduce memory footprint, but does not alter the underlying model architecture. So we need to solve the structural bottleneck limits for it. So we conduct on the model level profiling on the right entity. So as shown is described in this table, we on the right entity into 8 precision, the feedback network accounts for about 60%. Sorry. PyTorch format is, in case of the PyTorch format, is accounts for 50%, and LiteRT is the 60% respectively. And also we conduct on the other models, Java 3 and QM model. This model also feedback network models is already shown. So in this case, Gemma model, in case of the Gemma model, FFN accounts for 45%. So this motivation brings us to our proposed method. We name it activation guided feedback network distillation. Our AFD consists of these three components. Step one is the activation guided instrumentation. Step two is the per layer of site distillation. Step three is sequential layer training. So step one is the activation guided initialization. For each of the FFN layer, we score every layers by this invariable activation magnitude or calibration data. So after that, the input transpose is the expected product of the gate activation and the projection output. So we retain the top K neurons and directly initialize the compression model for those selected weights. So we compare the random initialized method. So our activation guided method leads to a good starting point from the distillation point. Step two is the per layer percent distillations. In this case, each layer is trained independently against the horizontal load. You use the cosine similarity, cosine distance as the loss function rather than L2 and KL divergence. Step three is the sequential layer training. In this step is include the layers are trained in order from end to end. After each layer is trained, the compressed model immediately replaces the original. So this figure shows our proposed method. So we only consider the people network. So our proposed method only includes the people network training. So we only train the normalization layer of people network and light people network. Light people network we only set the intermediate humidity dimension is changed. So the light FFN in weight initialization is activation guided based on the activation guided initial point. This chart shows Pearl analysis on Llama 3.21 billion model, cosine similarity and COQA upon score. So this performance when a single layer is modified isolation. So the red line, the red line is the COQA performance, and the red line is only block skip peak. And in recent methods, mostly webpack network compression method is block skip peak. But our lightweight model is when applied the 1 billion model, the earlier layer are particularly critical because they establish the fundamentally contextual representation. So skipping them caused very worse degradation, performance degradation. So our method constants the performance when our proposed method. So this section is model configuration. So we use the Llama 3.1 billion is the best selection of the model configuration. So we and the compression configuration is as follows. So we are dimension is the 2000 and the intermediate dimension is 8000, but we compress the half size of the 4000. So when you apply our method, so in parameters is about 37% reduction. So we are training as 100 posts per layer, and optimization and cosine learning rate scheduler. So we use the clever data set and about 1,000 sample sequence from C4 dataset. So we are only we evaluate the inference time and benchmark performance is evaluated on the Raspberry Pi 4. So this result, this is the main result of this paper. So under identical grain conditions and such as model pile and same precision time, our AFD constantly improve the TPS and challenge scores over baseline. So this case in interpol light configurations of with our method is the best score in this configuration. So this is several studies. So we apply the page selective active model analysis. Baseline is the non-use the AFD. Primitive APD is only use the AFD. AFD applied in the only previous stage only. Default AFD means that only default stage only. Both of the prevalent both sides, both of the applied. So in this case, we are in default AFD cases is the best performance. So And we will conduct on the parametric size of the data size, which is the 1,000 data set is the best performance for response point. And so we are publishing studies on the random iteration versus expression guided and possessibility versus heterotype tools. So we are best performance is set the expression guided initialization and possessibility distance. So in this case, is the or our method shows the overall the generalization across the overall volume, Quen 3 billion and 3.23 billion and Gem 3 1 billion. So in our method delivers the consistent GPW across overall model and challenge score with small performance degradation. So in this case, we cite the empirical practice in virtually transform-based economy LLM models on Raspberry Pi 4. So in this case, we are in the predictive analysis. So in this case, it's both objective cases. So question is why people perspectives, both the baseline and the general eventually accumulated where mobile against the response. So what's that creates the print of the picture generation is fully featured at the empty. So we need to reach point. So the first one is why structure convention regions fundamental clearly the actual space is non-linear. So in this case, we use the hardware vectorization and memory time patterns of the kernel. And second one is the inherent hallucinations. And they compress the pre-network, P1 and 4 layers with modifying the attention mechanisms or the model probabilities. So in this case, we are not considered the attention mechanisms, so we need to consider the attention mechanisms with our method is the best point, better point. Last one is the right heart is the static heavy patches sizes. Right heart in case of the right heart is right heart free or locate the heavy sizes. Based on this or low sequences, and early offense is size is targeted. Moreover, the locate size is more bigger, TPS is more flowers. So we are in summary of the paper. So this is all the end. So this presentation. Thank you.
Okay, thank you for the presentation. Do you have questions? And if we have questions, yeah, so just let me know because it's very difficult to hear what happens at CVPR.
Because this is only related to devices with only GPUs, right? Because I need to go to a GPU device and will not be about that.
Yeah.
That's the idea.
Yeah.
Oh,
And the challenge is only consider the Raspberry Pi 4. Raspberry Pi 4 only include the only consist of the CPU. Not CPU.
and so I think the method applies for any like device with only a CPU.
Yeah. Any question?
So do we have some other questions? Okay, seems like no. Okay, then we are moving to the next presentation to Realis Mobile High Fidelity Image Generation and Inference Acceleration System for mobile devices using realistic vision. Do we have presenter?
Okay, so can you hear me?
Yes, I can hear you.
Okay, so can you hear this right?
Yes, we can see, yeah, the presentation and can hear you.
Okay, so good afternoon, everyone. Thank you for attending this workshop presentation. And I will present our work realism mobile high-fidelity image generation and inference acceleration system for mobile devices using realistic vision. And our work focuses on a practical but important problem: how to deploy high-quality stable diffusion image generation on mobile class hardware. And this presentation is organized into 4 parts. And first, I will introduce the motivation and explain why deploying diffusion models on mobile devices is challenging. Second, I will present the realism mobile framework. And third, I will show the experimental results, including image quality, stability, and runtime performance on Apple M4. Finally, I will discuss advantages, limitations, and future direction of this work. Stable diffusion has become a powerful image generation framework and can produce high-quality video content from test prompts. However, most high-quality generation pipelines still rely on cloud GPUs or desktop-level GPUs. And therefore, our goal is to build a practical framework that makes stable diffusion generation more suitable for mobile deployment. And now there are 4 main bottlenecks in mobile diffusion deployment. And the first one is storage. Stable diffusion models usually occupy several gigabytes, which is still heavy for many mobile devices. The second one is computation. The unit needs to perform repeated denoising steps, which makes inference slow on mobile processors. While the third one is power consumption. Long inference time can cause heating and rapid battery drain. And the fourth one is compatibility. Different chips and inference backends support different operators, so a model that works in one environment may not directly work well in another. And our work makes 4 main contributions. First, we adopt realistic vision V5.1 as the base model to improve photorealistic vision and generation quality. And second, we analyze scheduler choices. We use DPM 2 plus 2M carriers during deployment for efficient sampling, while using DDIM during deployment for better compatibility. And third, we propose the golden state strategy, which generates multiple candidates and selects best one to reduce low quality outputs. While fourth, we import an ISP system Onyx to CoreML deployment pipeline for Apple M4 chips. With this pipeline, Onyx to CoreML achieves 15 seconds per 512 by 512 image, giving a 1.53 times speed up over 5000 PS. And the final FP16 Onyx model size is about 2.0 GB. And the Golden Seed improved the generation success rate to 85%. And this slide briefly reviews the stable diffusion pipeline. First test prompt is encoded by the clip test encoder, and we know that the diffusion process is performed in the latent state. The unit repeatedly denoises the latent representation according to the test condition and the sampling timestamp. And finally, the VE decoder converts the latent output into the final image. So this is our overall realism mobile framework. The input test prompt is first processed by the clip encoder. Then latent noise is denoised by the unit and scheduler. After denoising, the VE decoder generates the final image. On top of this standard diffusion pipeline, we also add as a golden seed selection model. Instead of using only one random seed, we generate multiple candidate images with different seeds. Then we evaluate the candidate and return the highest quality result. This framework integrates image quality, sampling efficiency, generation stability, and deployment compatibility into one complete pipeline. Well, our first model is model selection. Although SD 5.5 and SD 2.1 are strong general purpose models, they may still produce unstable details in photorealistic generation, especially in lighting, homogeneity, material and skin composition. Therefore, we use the realistic vision V5.1 as the base model. It's fine-tuned for photographic style generation and provides a stronger quality foundation. We also use SD2A to SD2MSE decoder to improve reconstruction quality. And from the evaluation results, realistic vision V5.1 achieved a realism score of 8.1 and a user preference of 45%, which supports our model selection. The second model is category design. During the development and real generation, we used TM2 plus 2M canvas because it can reach strong image quality with fewer sampling steps, and this improves sampling efficiency and reduces generation time. However, for deployment, we still use DDIM as the main scheduler because it is more stable and easier to reproduce in honest and core ML environments. This is an important engineering trade-off. So our design balances sampling quality, inference efficiency, and deployment stability. Now the third model is the golden seed candidate selection strategy. Diffusion models are sensitive to random seeds. Even for the same prompt, different seeds may lead to very different results. Sometimes a single seed may produce artifacts for composition or weak test alignment. To reduce the risk, golden seed generates multiple candidates while using different random seeds. And here, each candidate is called by a weighted function that considers athletic quality, test adherence, and technical quality. And the fourth model is the deployment pipeline. We first convert the PyTorch model into FP16 honest format. The model is exported in a modular way, including the clip test encoder, the unit diffusion model, and the V decoder. This modular export reduces memory pressure and improves portability. When the Onyx model is deployed through CoreML on F4 chips, we choose FP16 instead of 4-in-8 because the unit is repeatedly affected during denoising, and the int8 quantization errors can accumulate over multiple steps. This may lead to visible color drift or degraded image quality. And finally, we also use split some attention to better match Apple acceleration paths and improve hardware utilization. For evaluation, we construct a benchmark set of 200 test prompts. These prompts cover 7 scene categories, including portraits, animals, food cityscapes, landscapes, architecture, and some still life. For golden seed evaluation, each prompt generates a candidate images, and the runtime benchmark is conducted at 512 by 512 resolution. We evaluate the system using athletic score, clip score, realism score, user preference, and inference time. And here we compare the realistic vision V5.1 with several stable different variants. The left chart shows the realism score. Realism vision V5.1 achieved the highest realism score, reaching 8.1, while the other models are around 6 to 7. The middle chart shows user preference, and again, realistic vision V5.1 obtained the highest preference, reaching 45%. And here we can see this result shows that the base model selection has a strong impact on final generation quality. And this slide compares the efficiency of different schedulers from the curve DPM to plus 2M cover, which strong athletic quality with fewer sampling steps. At around 20 to 30 steps, it already achieved competitive real quality, and this makes it useful during deployment and real result generation. However, for deployment, we still keep TBIM as the main fallback because it is more stable in ONNX export and core ML representation. So the circular design is not only about image quality, but also about deployment robustness. And here we evaluate the effect of class field-free guidance skill. If the CFG skill is too low, the generated image may not follow the text prompt well. And if it's too high, the generated image may become less natural, and the athletic score can decrease. And after some experiments, we use CFG 7.0 as the final setting in our experiments. What's more, we also evaluate the effectiveness of coding speed compared with single seed generation. Coding speed reduces the low quality generation ratio from 40% to 15%. This corresponds to a 52.5% percentage reduction. And the average athletic score also improved from 6.32 to 6.71. The curve shows that the athletic score and success rate improve as the number of candidates increases. And last, here shows the multi-backend runtime benchmark on Apple M4. PyTorch CPU takes 135 seconds per image, which is too slow for practical use. Onyx CPU reduces the latency to 68 seconds, showing the benefit of graph-level optimization. PyTorch MPS, which uses Apple Metal GPU backend, takes 23 seconds an hour. Onyx to core ML pipeline further reduces the latency to 15 seconds per image. And this means Onyx core ML achieves a 1.153 times speed up over PyTorch MPS. And this slide shows representative real results generated by Realist Mobile. And the evaluation shows the contribution of each component. When coding seed is removed, the low quality generation rate increases and the athletic score decreases. When the circular is replaced, more inference time is required to achieve comparable quality. When the base model is replaced, realism and analytic both decline. When FP32 is used instead of FP15, the quality gain is small, but storage and latency increase significantly, and therefore the components are complementary. To summarize, we have four main advantages. First, it improves the quality, and second, it improves efficiency through circular design and speed in deployment. And third, it improves stability through coordinated candidate selection. And fourth, it improves portability through the Onyx and Core ML deployment pipeline. The key point is that Realist Mobile is not just a single acceleration trick. It is a complete system that integrates quality, speed, stability, and compatibility. And there are still some limitations, such as the FP60 model size is about 2 gigabytes, which is still large for some mobile devices. And the second, the 15 steps may seem longer than we need. And third, golden speed improves generator stability, but generating it content increases latency significantly. And fourth, TPM2 Plus still has compatibility issues in some Onyx export settings. And these limitations do not invalidate the system. Instead, define clear directions for future optimization. And our future work may focus on making the system smaller, faster, and more widely deployable. First, we will explore next precision quantitation. And second, we will investigate few step generation methods. Third, we will further optimize neural engine utilization. And finally, we plan to extend the framework to more mobile platforms. And here are some main takeaways, such as it can balance quality, speed, stability, and compatibility, and so on. And the result shows that a carefully designed deployment pipeline can make high-fidelity decision generation more practical on mobile class hardware. Okay, and that concludes my presentation. Thank you very much for your attention, and I would be happy to take any questions. Thank you.
Okay, thank you for the presentation. Yeah, good targets for follow-up work. Do we have any questions? Okay, seems like no questions. So in this case, again, thank you, and we are moving to the next talk, which is Edge DIT, hardware aware diffusion transformers for efficient on-device image generation from Samsung Research. Do we have somewhere? Do we have the guys here online or on site?
Yes, we are just preparing the on-site presentation
Yes,
here.
and make sure that the presenters they use their own microphone, because with the previous talk it was very difficult to understand what the speakers were talking. So probably you should just mute your microphone, and the microphone on the laptop of the speakers should be enabled instead.
See it on the screen?
So we can't hear anything right now.
Yeah. Andre, is it audible?
It's a little bit better, I think. But we still probably won't hear you once you start talking, once you start the presentation. So can you enable your own microphone, as a microphone on your laptop?
Do maybe is try this here, you put somewhere.
Yes, this should be much better.
Okay. Andre, is it audible now?
Yes, it's perfect.
Okay, thank you. So good afternoon, everyone, and welcome to this session on Edge DIT, hardware-aware diffusion transformers for efficient on-device image generation. So this is a work jointly done with my collaborators at Samsung. I'm Srinivas Meriala, and the idea of this work is to take the DIT model, that is diffusion transformers, and optimize this architecture for the deployment on the edge devices, such as the Snapdragon chipset on the Samsung Galaxy smartphones. So the idea is the edge imperative. That is, we want to take the models onto the deploy them on the edge, because to eliminate the latency between the cloud and device transfer and ensure there is a privacy between the for the user. And also at the same time, once we ensure that these models are deployed on embedded devices, that they can have massive applications compared to the costly GPU clusters. Now, while we have this as our goal, there is a lot of bottlenecks present here, the challenges present here. That is, if we take a DIT kind of a model, which is having 675 million parameters, that model will consume massive amount of memory on the embedded devices, which are already resource constrained. So the idea is that if we can try to optimize this model with respect to any kind of complexity parameters, such as flops or parameters alone, that would not be sufficient for measuring the on-device key KPIs, that is key performance indicators. We ensure that in our search strategy, we take the NPU latency, that is we deploy the candidate designs on the smartphones and measure the NPU latency, and then that latency is sent as a feedback to the optimizer to perform the search. So our approach is that we first take the architecture and conduct a network surgery, and this network surgery will provide us with respect to the different kinds of blocks present in the entire model, which are either consuming a lot of latency or memory. Now, after we find out that kind of blocks, we perform a sensitivity analysis with respect to the trained weights. That is, if these blocks are robust to the variations in the weights, then we would consider them to tweak and replace with certain mobile-friendly or hardware-friendly alternatives. The blocks which are extremely insensitive, that is, the accuracy loss is severe, we won't touch them during the search strategy. So once we identify these blocks become our dimensions of our search, and we implement a hardware-aware design of different surrogates or different alternatives, which I'll show in the approach here. And once we prepare that list of hardware-aware search space, we perform a feature-wise knowledge distillation. The surrogates that we are building will ensure that they are fast on the hardware, but since they are not trained, there will be severe drop in the accuracy. To mitigate that issue, we are ensuring that we have the feature-wise knowledge distillation. Once we build these surrogates, the entire problem now becomes a combinatorial optimization problem with a lot of parameters, a lot of options or candidate architectures, and therefore we implement a optimizer. And any off-the-shelf optimizer could be employed here because there is no end-to-end training during the search, but we here implement the multi-objective Bayesian optimization, where one of the objectives is the latency itself, and the second objective is the accuracy of the model. So now I'm going to describe how we are determining each of this search spaces, how we are designing the search space, and then we will move on to the surrogates which we are building on top of this. So the first search space that we are building is we have taken the DIT Excel by2 model, which has 28 blocks. Now we are trying to replace or fuse 2 DIT blocks into one. So as we can see here, 2 of these are fused into one. And similarly, these 2 are fused into one. Now, it is not possible to fuse all of them into a single blocks. And therefore, that is what we have to find out through our optimization search, which of these 2 blocks or pairs can be converted into a single DIT entity, a DIT block. So while there could be a question or an ablation study that why only 2 of them can be fused into one, we have done that here. So up to 2 blocks, if we take the accuracy, the sensitivity analysis shows that it is intact. But if we take any more blocks and convert them into single block, the accuracy drop is severe. So we cannot go for fusing 3 blocks or more. We have to stick to 2 blocks and convert them into a single block. Now, when we do that, since there are a total of 28 DIT blocks in the network, that is 14 pairs, we have a total 14 dimensions in the search space. Now, for each of this dimension, either one of the alternative could be to retain the pair as it is or to replace it with a single fused DIT block. So there are 2 candidates for each of the dimension. The total search space size therefore becomes 2 bar 14. Now, this is the first stage 1 of our search space. Moving further, in addition to this, what we have implemented is we have taken each block and tried to design some aspects, some hardware-friendly options to this. In that, one of the mechanism is the feed-forward network ratio. So the feed-forward network expansion ratio is fixed at 4. We tried multiple variants of that. That is 1, 2, 3 as an alternative. So here in the ablation, you can see that if we take an MLP ratio of 1, once again, it destroys the accuracy very badly. So we don't want to consider it during our search space. Whereas MLP ratio 2 and 3 give us images that are very similar in image quality. So since the image quality is similar for MLP ratio 2 and 3, we stick to the MLP ratio 2 because it would reduce our parameters. So that is the reason why we have the options as 2 and the original one, which is 4. So these are the 2 candidates that we have designed with feed-forward expansion ratios are fixed at 4 and 2. In the other mechanism which we are implementing here, what we do is we tweak around with the attention dimension. So attention dimension is, in the original model, it is 1152. We scale it down to 512 as the other alternative. We also did an ablation study to check whether 512 or 768 can give similar accuracy. And since here we can see that anything lower than 512 was destroying the accuracy, whereas 512 and 768 resulted into similar image quality. So we stick to 512, which is the lower value amongst them. So again, we have 2 options here. 1152 is the original and 512 is what we have selected. So the previous one, which is 2 options here and here again 2, gives us 4 alternatives for each of the 28 blocks. So that makes 4 bar 28 as our total candidates. So from stage 1, we have 2 bar 14, and from stage 2, we have 4 bar 28 candidates. So this is a challenge over here is training these candidates individually is computationally impossible. So what we do is we perform something called as feature-wise knowledge installation. So here essentially we take a teacher block from the original model, which is trained for the generative ability, and we distill the features of that particular single block into the alternatives that we have prepared. So it's not an end-to-end distillation, but only a feature-wise distillation. After we perform that, we do a pruning of the blocks which have resulted in a very bad accuracy, and that way we would get the hardware-aware search space, which will be left with only our candidates into the search space. On top of that, we implement this kind of a Pareto optimization with two objectives, where edge latency is one of them, because for each of these alternatives that we have taken, we profiled these blocks on the device and got the edge latencies. So cumulative latencies of the entire network would be a good proxy to the original latency profile on the device. So we take that edge latency, we want to minimize it, and FID is the other objective, which is objective representing the accuracy. It's just a forward flow, so there is no end-to-end training in this search. We want to minimize even this FID. So the Pareto front would be formed in this manner. Among these, we got almost like 6 different candidate architectures. The HDIT1 over here, which is lying here, is the most efficient in the sense, efficient in terms of the on-device KPIs, but the least accurate amongst all the candidates. HDIT6 is the one which is most accurate, but least efficient on the on-device KPIs. So this is the Pareto optimal condition that we have got here. Now, we will see after we obtain these architectures, since we have used only feature-wise knowledge distillation, there can be a cascading loss of accuracy. We do a full end-to-end fine-tuning of these selected architectures, the Pareto architectures. And after that, we found out these results that there are almost 30% reduction in the parameters. And we profiled this and we performed the entire analysis with respect to the Qualcomm 8850 NPU. And we observed that when deployed on the Galaxy S25 Ultra, we have 1.65-fold improvement in the latency. Not only that, we also show that this approach that we have implemented does not restrict itself to the Qualcomm type of chipset. We deployed the same model on the Apple A&E on A18 Pro, and we are observing there 1.45x improvement in the latency compared to the base model. And there is, of course, reducing the on-device KPIs is also reducing the theoretical complexity that is measured in terms of Gmax and Gflops. So overall, we are coming up with a generic approach which can design these architectures for the mobile AI, mobile hardware inference, AI inference. So we observe that while we need a particular hardware to start with for profiling, it can extend and be used to portable to the other hardware as well, such as, for example, Apple, and thereby making this approach hardware agnostic. Finally, we wanted to see the qualitative measurements of this. So we observed that the models that we have obtained in terms of the Pareto optimized models were resulting in a lower FID when tested on the entire data set. So this is another important aspect which shows that not just the network design is relevant with respect to the accuracy. We need to design it optimally in a fashion that we have come up here that can give us both improvements in accuracy as well as the on-device KPIs. Finally, these are some visual comparisons which show the comparison between the DIT XL/2 base model and HDIT1 and HDIT6. So this again confirms that the structural simplifications that we have engineered for the mobile NPUs, they do not sacrifice the expressive capacity. Now this becomes a new backbone or foundation model which is optimal for the hardware. And on top of this, it can be fine-tuned with different LoRa's or different kind of adapters for different use cases. So the conclusions is that we have come up with a method that can take an existing state-of-the-art model and convert it into a hardware optimized model without losing on the accuracy or image quality. And by abandoning the brute force pruning method, there are multiple pruning methods. We have come up with this hardware-aware search space, which is the crucial or the heart of this entire approach. And we made sure that it is end-to-end training free. Thereby, it's a very quick solution that we are obtaining within a week's time on models such as DITs, diffusion transformers. Finally, since we are able to deploy these models on the embedded devices, the privacy of the user is preserved, speed, of course, is ensured, and then image quality is also properly met with. So that's the QR code for the full paper. And thank you for the attention. If there are any questions.
And yeah, thank you for the presentation. An interesting talk. So do we have questions? Okay, seems like we don't have questions on site, right?
The next one.
Okay, then we're moving to the next talk, also from Samsung Research, which is quantization with unified adaptive distillation to enable multi-LoRa based one-for-all generative vision models on edge.
Thank you, Andre. So this is our second paper from our team where we talk about the deployment of the large vision models with multiple LoRa's adapters specifically tuned for multiple use cases, converting that into a one-for-all generative vision model. The challenges associated with its deployment on the embedded devices and how do we mitigate those issues. So that is the talk over here. And moving further, so essentially what is happening is that we cannot have a single vision model for specific to one use case. So we need to have a one model serving multiple use cases. So we can achieve that, as you all know, on the server using LoRa adapters. Now, the problem is not evident or clear when it is only on the server. The problem comes when we try to deploy it on the device, embedded device. So as you can see here, what happens during the deployment on an embedded device is the AI model, which is consisting of the graph as well as the weights which are present, which are converted into the binaries, gets deployed on the device in form of a frozen graph and bin file. Now, when we have this as a frozen graph and bin file, we do not have the luxury to modify the weights of the foundation model on the flow during the runtime. That is the major bottleneck. This bottleneck is not present when we deploy the models on cloud. On servers, we can instantaneously change those weights by just implementing the LoRa logic. But here, we cannot do that because the moment the LoRa weights come in, there is no way we can change the binary, the frozen binary of the foundation model. So once this is the bottleneck that we are presenting, this kind of breaks the entire LoRa philosophy. That is, we no longer have a weight update mechanism that can shift the model's capability from one use case to another use case. This is only because of the static graphs that are present when we deploy either on the NPUs on the Qualcomm chipsets or on the neural engine on the Apple chipsets. So in both the cases, we have this issue with the static graphs. They are not dynamic. The weights cannot be changed. So how do we mitigate this issue is what we are going to discuss here in the first part. The second part is, as a consequence of that solution that we are getting, there is another new problem that is arriving, which is because of the quantization. And that is also solved in this particular problem. So the core innovation that we kind of treat here is we prepare, as I said, the original model, the foundation model as a single graph itself. But then to the single graph, we can take the inputs, the activation maps, which usually become as inputs, that is present. Now, the LoRa weights which we have with us are of the size of 10 MB to maybe 15 MB, which is same as the size of the original inputs which are given to the model. So we can treat these LoRa weights as an input to the graph itself. Rather than treating them as a frozen weights, we treat them as an input to the model or an activations. Okay, so these weights are becoming activations to my model. And once those input is fed, during the logic of the graph execution, I make sure that the weights are updated with the new LoRa which is coming in. So what this does is it kind of allows me to dynamically switch from one task to another task or one LoRa to another LoRa during the execution or the runtime. So this is a massive advantage which we get, which was previously not present. If we don't have this kind of a mechanism and treat one single LoRa as a separate entity from another LoRa, then we need to build multiple graphs for different use cases. And if we build multiple graphs for different use cases, they all boil down to multiple large vision models for multiple use cases, which is not possible to be deployed on the device. So this is the way in which we are able to make sure that as the LoRa weight is coming, LoRa1 weights are coming, it becomes an input to the model and it gets it's able to modify the weights of the foundation model itself. But then this causes an issue with respect to the quantization. As we all know, during the quantization exercise, we have these parameters, which are basically the quantization parameters, 0 point and offset. For the inputs which are coming into the model, which we treat as activation maps, these activation maps, the quantization parameters are decided before. Again, on the NPUs, we cannot have dynamic quantization. We only have a static quantization. When the graph is deployed along with the binaries, we make sure that the quantization parameters are enforced or encoded into that graph itself. It is frozen over there. So now the problem, what we are seeing, observing is that we have taken care of the input to the model, original input to the model. But since LoRa's are now coming as an input, additional secondary input, and these LoRa's are entirely different. Like, for example, if we take these real use cases, one is, say, the in-out painting use case, and the another one is wallpaper. Like, this is an entirely two different pipelines. So in case of wallpaper generation, the user would give an image to the pipeline model and ask it to generate a wallpaper based customized to that particular image. In in-out painting, it's like circle to search feature which we have in the Galaxy phones. We want to eliminate a particular object or entity from the entire picture. So these are two entirely different use cases. The LoRa 1 will serve for wallpaper case, LoRa 2 will serve for in-out painting case, while the foundation model is same for both of them. Since these LoRa's are entirely different, their distributions will also be completely different. And since those distributions will be different, the quantization parameters which will be there for LoRa 1 will be entirely different from LoRa 2. So the question now comes is, with which quantization parameters will we freeze the graph? That is the bottleneck. That is the problem which we are suffering with here. And to solve that problem, what we have done is, after the LoRa's are developed and are prepared for deployment, we kind of take these LoRa's, we perform a sensitivity analysis across all the LoRa's, okay, which is done offline before deployment. We perform the sensitivity analysis, find the most sensitive LoRa. We determine the quantization parameters of that sensitive LoRa, say, for example, this one over here, okay, and that is done by simple post-training quantization method. We get the encodings, that is quantization parameters for the LoRa weights of, say, LoRa 1 or the wallpaper. Now, what we do is we put these encodings as constraints for the second LoRa. That is, when I try to quantize this using a quantization aware training strategy, I implement a quantization aware training strategy, which is slightly modified to have a knowledge distillation based pipeline. So when I do this, I make sure that my quantization parameters for LoRa 2 are coming out to be same as the quantization parameters of LoRa 1. This is only possible if we fine tune the LoRa 2 or any other LoRa's that are present in future, for example, the LoRa 3. So that is what we are proposing as the quad framework. So the way we do it is either using the PyTorch quantizer or libraries such as AIMet from Qualcomm. So there we prepare a quant-sim model, which is a quantization simulation model. There, while the knowledge distillation is employed and the weights, the LoRa weights are fine-tuned again, there is a constraint, that is, they all have to fall back to the 0 point and offset of LoRa 1, which is the most sensitive LoRa amongst the bunch of LoRa's that we have got. So once this approach is implemented, we can further fine tune. I mean, this is just one of the losses, MSE loss or the knowledge distillation loss is the one loss. We can add other auxiliary losses such as the original training of LoRa 2 or any further losses like regularizations can be added to make sure this training procedure becomes robust enough. With this, after this is done, now LoRa 2 and LoRa 1 will have the same encodings, which are exactly same as the most sensitive LoRa's quantization encodings or quantization parameters. We freeze the graph with that quantization parameters. Now, and then once we deploy it and say at future release of the model, once again, we have a new use case. And for that, we have, say, a new LoRa 3. Now, in that case also, we can perform the same quad framework. But then at that time, we have to give the encodings with which the graph is frozen as the condition or constraints during knowledge distillation. So this is exactly what we try to do and make sure that multiple LoRa's are coming out into the same quantization parameters. And then we freeze the graph And this graph takes LoRa's as inputs and gets deployed on the device. So this is a stack describing the entire process which is happening over the mobile phone. So there is a LoRa deserializer, which is actually containing the LoRa bin files. And we are giving that LoRa as an input to the unit over here. This is described for the unit stable diffusion based model, but it is applicable to any other recent most diffusion transformers as well. Basically, the LoRa's have to be sent in as an input. And then we have the other aspects which are present, like the pre-processing and the post-processing units in the pipeline. They're intact, they're not changing. And we have the sampler that's also exactly same. So the only difference over here is the LoRa is now coming as an input, and that based on this input, the corresponding use case can be done. So for example, this is prompt guided image transformation or wallpaper generation, and this is an object eraser. So based on this particular LoRa as an input, these two can be switched dynamically at the runtime. So these are some experimental results that we have over here for the prompt transformation, that is wallpaper generation and object removal use cases. We observe that the cosine similarities of the W8A16 quantized model and the FP32 model are at 0.94. The FID score for object removal is at 5.5. So we basically show that it is a near lossless generative fidelity maintained entirely on the device. Going further, we show now that it is not just a specific, the generic nature of the approach. It is not just specific to the Qualcomm chipsets. We extend this approach on, say, for the servers, like by doing it on completely open stacks such as PyTorch, then doing it on Qualcomm, that is AIMed. Then we are doing it on Exynos chipset. So LSI is for the Exynos chipset and also for the MediaTek chipset. So on all different chipsets, this particular approach has been implemented, and not just for a couple of use cases. We have gone to 10 different generative AI use cases. So in all these cases, we can see the reduction in the memory because of having a single unified graph. And here we present the comparison between Qualcomm, LSI, and MediaTek with respect to different parameters like the RAM and peak RAM usage during the deployment. So that is what we had in this session, basically to show how we can have the philosophy of LoRa, which is now considered as the most useful trick on the servers, is not that straightforward when we take it onto the devices because of the static graphs and frozen quantization parameters. So to mitigate that issue and ensure that the quantization happens for all the LoRa's in a uniform way, and dynamic switching happens between multiple use cases during the runtime, this quad framework will be most essential. And we also show that this framework is, once again, agnostic to the hardware. It can be useful for multiple chipsets. Thank you. Thank you for your attention. Any questions?
Thanks a lot for the presentation, for practical approaches, and on-device evaluation. So, are there any questions? Okay, seems that no questions. Okay, then we're moving to the next talk, which is slimmable. Yes, thank you. Which is slimmable context with adaptive inference for efficient multi-device deployment. And as the presenter is online, can you start sharing the screen? So, Janek Haberer, on Zoom, can you start sharing your presentation?
And it should be like also, yes, yeah, exactly.
Mhm.
Hello, can you hear me?
Yes, we can hear you, but we cannot yet see.
Yeah, sorry, 1 second, just setting up.
Mhm.
To see whatever is yes.
Okay, perfect.
Yeah, everything is set up, right?
Yes, so we can see and we can hear.
Okay. Then yeah, thank you for having me. My name is Yannick Awa, and today I will be presenting our work Slimmable ConfNext with adaptive inference for efficient multi-device deployment. Joint work with a student of mine, Jon Eike Wilhelm, and my professor Olaf Landsiedel. So let's start with the motivation. So usually we deploy specialized models on devices with varying constraints. So imagine you have a bunch of devices. So we have maybe some kind of server, we have some kind of desktop or laptop, and also mobile devices such as smartphones, or technically we can go even further to IoT sensors. Yeah. What we usually then do is that we kind of train a family of models and then, yeah, deploy whatever fits on the device. So, for example, for a larger server, but obviously this is a bit exaggerated now, don't burn me on this, but we might deploy some D8-based model or ConfNext-based model. Then for some desktop, laptop style of device, we might deploy some smaller models. And then for a smartphone, we might have some tiny models that we can deploy there. Yeah, what is the issue here? The issue is that we kind of have to train and store and maintain a separate model per device class or family. So that is something that's, I think, quite common that, yeah, usually we have to release some kind of family of models. Additionally, also the available compute can vary, especially for mobile devices. So that could be due to battery state, due to thermal throttling as well, but also for latency deadlines. So if you have some kind of requirements, you need to have some classification or whatever in a certain amount of time, you might have to speed up and get some result faster, right? And the issue is that these classic models, if you deploy it once, well, it is like a fixed amount of speed, more or less, right? So there's no way to switch easily to some smaller model, for example. I mean, sure, you can store multiple models on the device and then load the new model and then run the inference using that, but that also introduces additional overhead. So what do we want to do? We want to train a model that can scale its compute on the fly. So imagine you have some kind of base model, and then we train it in a way that within this base model, there's also a smaller model, and maybe even a tiny model. So it would kind of look like this. So yeah, you basically have one model, and you can also run it at, for example, 50% of the size of it. Yeah, in this case, maybe to quickly mention that here we are doing this not on the amount of layers, which maybe it looks like it, that we're doing this. It's with the width of the network. So we're kind of making the network slimmer and not shorter. But obviously that also exists. So there's a bunch of, I guess, like early exit style base lanes as well. Good. Yeah, and then basically we train it in a way that we get this type of model, and then at inference time we can basically just pick whatever model we need, depending on whatever constraints we have. And yeah, we don't have to reload any model, and yeah, we also don't have to do any additional training or whatever like that. In our work, we chose ConfNext to make that slimmable. Reason being that in the vision transformer world, there are already a few works doing something very similar to this, and these will also appear later on in the evaluation, because we kind of wanted to see how well does ConfNext perform in this type of scenario. Yeah, and what we have to do here is, so we have this basic ConfNext architecture, and what we have to do is we basically go into the ConfNext block, which is the majority of the network, of course, and we basically adjusted the code such that we can run each ConfNext block also only adds, for example, half of the capacity, so half of the channels essentially, or whatever other number you want. This is very arbitrary and up to how you want to configure it, obviously. And again, important here is that these weights are of course shared, and it's index based. So it's like the first channel is always included. The last channel is always the first one to be thrown out. And then, if you take 50% of the network, the first 50% of the channels are included and so on. For the training phase itself, it's fairly stupid and simple. So we basically just do random width sampling. So for every single forward pass, we just choose one random configuration, one random capacity or width, and just run the forward and backward pass with that. And then we just run it for how many epochs we want. And in the end, we get this model that kind of perform at these varying widths. Good. With that, we can slowly come to some evaluation. So I will show you that our model, this slimmable ConfNext, will achieve the best accuracy per Gmax. Unfortunately, we don't have any throughput or latency numbers yet. And we evaluated all of this on ImageNet 1K. So I have 3 graphs here because we tested this on the tiny, small, and base models separately, and also have corresponding baselines. And basically it's about accuracy versus the amount of Gmax required. So first, some baselines. These are vision transformer baselines that are also slimmable, you could say, or elastic. So these are also models where you get one single weight file, and then you can run these models also with, for example, only 50% of the weights. Namely, these are Dynabird, HydraVid, Matformer, and SortedNet. These are based on the base models. So these are all based on the DIT base model specifically, this architecture. And then we also trained these on the DIT small model as a base model. We have a variety of larger and smaller models. And now, we start with the tiniest model configuration we trained. So based on a ConfNext Tiny, we trained it with 3 different configurations. So one configuration is, it's called 3 sub, 4 sub, 5 sub. So sub networks is the idea here. So with the 3 sub network, it means we trained for these 3 specific configurations. It would be 25%, 50%, and 100%. 4 sub networks means it's 25%, 50%, 75%, and 100%. And then 5 sub networks means also 37.5% configurations in between the 25 and 50%. And as you can see, all of these 3 variants outperform the vision transformer based elastic models by quite a large margin. As a reference, there's also the ConfNext Tiny stuff. So that would be if you train ConfNext Tiny standalone. Our models here are trained for 600 epochs. Also, the baseline models are trained for 600 epochs, except for the ConfNext Tiny Star. That one was only 300 epochs. So now you might say, okay, but then obviously we trained more than them, and still somehow we are slightly worse than the ConfNext Tiny model itself. But we are getting this family out of it, right? So we have these trade-off points. We can also run it at much smaller width, which means it's much faster and more flexible. Then we also use ConfNext Small. Did the same thing again, 3, 4, and 5 sub networks. And here again, ConfNext Tiny and Small as a reference. And I think here also becomes a bit more clear that training ConfNext tiny and small for 300 epochs each versus our model that is 600 epochs in total, so that would be equal amount of training. You might not get the same peak performance, but you get this very nice trade-off, these intermediate models as well. And then for base, these are even more numbers. I think the biggest caveat or limitation right now is that we are always losing a bit out on the maximum accuracy here. So the models get slightly worse, at least at the 100, like if you run at full capacity at 100%. But the smaller subnetworks, I think, achieve very nice trade-offs of accuracy per Gmax at least. Then we also compared to some previous elastic CNNs because they also exist. But they were mostly trained on some older models such as ResNet or MobileNet. They usually also have additional mechanisms in there, such as some of them also use knowledge distillation in there as well, or they also need some switchable batch normalization. And this is the neat part here about ConfNext is that we don't really need any of that. So this is like fairly straightforward to train. And in the very small Gmax regime, they can kind of achieve a better accuracy per Gmax, but they kind of stop scaling up. So they can't really get much better. That's the caveat here. And then there's not really that conclusive to be fair. It's just tested on the tiny model with 3 subnetworks, but training for more epochs still increases kind of consistently for every single subnetwork the accuracy. So it's not like only the largest model gets better or the smallest one or something like that. They all kind of uniformly get better accuracy the more we train. How much more we can train and get more accuracy is a different story. Not sure about that. Would be something for future work as well. And then I think I will skip over the next slide and say, thank you all for coming and listening. I showed you Similar ConfNext, which I think is a strong nested CNN or elastic CNN, which outperforms previous elastic vision transformers in CNNs. Here are also QR codes to the paper and our GitHub. So code is also public. And thanks.
Thanks a lot for the presentation. Do we have questions?
Doesn't seem to be the case.
Yeah, well, it's a little bit complicated to ask questions because on site people need to come to the front, to stand in front of the laptop that is used for sharing these videos, and I guess the majority of people are scared of going and asking. Okay, good. Then thanks a lot for presenting, and we will now move to the next presentation, which is Mobile AgeNet, lightweight facial age estimation for mobile development.
Yeah, hi. I will share my screen and then Ashwati will present the first half. Is it visible?
Yes, you can see it.
Let me start the presentation. Hi, everyone. Myself, Ashwati Baiju. So we are planning to present this together, and I will start with this. So we are going to present our work on mobile AgeNet, lightweight facial age estimation for mobile deployment. Facial age estimation has numerous real-world applications, but deploying accurate models on mobile devices always remains challenging due to constraints like computation, memory, latency, and all. So in order to address this challenge, we proposed the mobile AgeNet, this framework, which is specifically designed for mobile deployment, and it's also able to maintain a competitive prediction accuracy. So we'll see this in detail. Next slide. The table of contents. So we'll start with the motivation behind this, and then the main architecture, the data set used, and the training strategy. And then we'll discuss on the experimental results, the qualitative results, and we have also performed an ablation study and the comparison with the existing models. And finally, we'll have a look into the deployment validation, how the model is converted into TF flight and the mobile latency. And to conclude, we'll see the future directions as well. So next slide. Why mobile age estimation? So facial age estimation is actually difficult because the facial appearance changes significantly across person to person, and we have a wide range of age groups, and also there are different imaging conditions. So we have to build a model that achieves a low prediction error, that is low MA value, and also here our target model is. So here our target device is mobile, so it should be lightweight, and also for the real world deployment, it is expected to have a low latency. So let's see if our model is able to achieve all these factors. First of all, it's a lightweight architecture, so we are using the MobileNet V3 large backbone, and we are also using a compact age regression head. We'll see this in detail in the architecture section, and this is only having 3.23 million parameters. And for the reproducible training pipeline, we are integrating this into the NN-Lima framework so that it ensures a reproducible evaluation and training setup. And finally, for the deployment validation, we are converting the model into TF Lite, and it's able to achieve around 14.4 millisecond latency. Now the data set and the evaluation protocol. So for our model, we are using the UTK face dataset, which is over 20,000 face images are there, and the age ranges from 0 to 116 years. And also in our work, we are considering this as a regression problem. And on the right side, you can see we have the UTK face dataset, and initially we are performing some data cleaning, and then an age split is performed into train, validation, and test set in 7:10:20 ratio. And we are using the primary metric as the mean absolute error. Now let's have a look on the architecture used. So we can see the pre-trained MobileNet V3 large backbone is used. So this is a pre-trained model, and it is having a sequence of convolutional and inverted residual blocks as backbone. And here, this is basically used for the feature extraction, and here a facial image when it is processed as input, and this initial block extracts all the visual features, and these feature maps are then we are performing a global average pooling on this, and we are compressing it into a more compact representation, and then we have a lightweight regression head. And here we have the fully connected layers, and here the actual learning happens. And finally, we are using a bounded age prediction mechanism and also a sigmoid age scaling so that whatever predictions are there, it is estimated into a realistic age values. So this is the basic architecture. Now let's discuss about the training strategy.
Yeah, so from here, I'll take it up and then I'll explain you how we trained our model, how we use these strategies, and what actually we got it at the end. So we followed the two-stage transfer learning strategy, where the first one is we took the backbone of mobile net version 3, and then there we trained it for the to find the best hyperparameters using the optuna. So that's our first stage, where we use the back frozen backbone, and then we did some hyperparameter search, and then we got the best hyperparameters. So in the frozen backbone, as you can see, the first five epochs are frozen, and then it continues to till 100. And in that whole process, we got the best checkpoint at epoch 95. And on that epoch, we got the our validation MA on the validation set. So here we'll show you what we got in that process. So that MA is on the test set, the 4.65 years, which initially you saw the 20% split in the test set, and the parameters of that 3.23 million with the GForce values there. So these numbers we got on the best epoch checkpoint. And then we also run into the second phase, which is the final training thing, and then we got these results. As you can see, it's like true values and the predicted values. So as you can see, our model able to predict like with the range of our MA. So to improve these, we also did some ablation studies. So in the ablation studies, we use the flip method. So we use the horizontal flipping, which improves our MA from 5.5 to 4.7. And then later we use the stable bounded regression as well, and fine tune the model, which allows us to achieve the final MA of 4.65. So we only use the one ablation study here, but we also tried different one in our research. So basically, we try to find out more parameters, more hyperparameters we tried, but this one is the best one we found. Then we also compared our model with the existing methods. So here you can see our model is getting 4.65 MA, and whereas others are getting 5.44, 5.74, and 5 respectively. Here's the only difference is that the other models specifically didn't mention anything about their flops or their parameters or how they are splitting. So in our case, we are clearly mentioning in our paper how we are taking the training data set, how we are taking the validation set or the test set. So it's clearly mentioned there how we are approaching the data pre-processing steps and then the full architecture training. Also, we make sure like our model is the mobile friendly, because we tried to convert our ONNX model to TF Lite, and we also implemented that. And here you can see we didn't get any loss there. So on ONNX we got the MA of 4.83 on the validation set, and then we converted it to the TF Lite, and we got the same MA without losing any without losing any more error. So here you can see our model size is just 12.34, which is very good to deploy on the very light mobile devices as well. So uh, we also we also use this whole pipeline, like the pipe we took the on and export, and then we converted it, and then we tested it on the real mobile device as well. So here you can see the latency analysis on the real mobile device, for which we use the AI benchmark tool is provided by the workshop. So here you can see our average latency is around 14.4 ms, and the initialization time is around 25.6 ms, which is really good because in most of the cases it range around 15 to 20 ms, and we are getting almost 14.4 ms. Here you can also notice one thing, like with this latency, you can say like when we actually deploy this model on the real mobile devices, there will be slight difference, because in the real mobile devices there will be more specific things we have to take care, face detection, real face detection to the final result. So maybe it will increase, but this is the actual result we are getting on our Android device. So now what next? So here we have some few takeaways. We are getting the full 4.6 MA on the full range of UTK phase, which has more than 20,000 samples. Then we're also getting the real-time mobile inference, which is really good to deploy it on the real mobile devices. And there is no accuracy loss when it actually we are converting from ONNX to TF Lite. So in the future work, we can use the knowledge distillation where we can train a teacher model and then we can train more small models using the knowledge distillation methods. And also we can move with the in-state quantization to actually deploy it on more mobile devices. And then other thing is that the multitask facial analysis, because right now it's really hard to predict the age of the children or maybe the older one. So for that we can use the multitask facial analysis where we can actually extract the accurate features and then we can predict the approximate age of a person. So uh, yeah, so that's it all about our mobile age net model. So if you have any questions, so we'll welcome them. Thank you.
Thanks for presenting your work. Do we have questions? Yeah, probably no. So then we're moving to the next talk, which is that clip, generalization aware compression and geometry preserving continual learning for vision language models on edge devices. And I can see the presenter online.
Hi, everyone. Can you hear me?
Yes, we can hear you.
Okay, let me share my screen. Hi, I'm Kai-Qi Zhao from Efficient AI Lab at the Computer Science and Engineering Department of Oakland University. Today, I will present our work titled The Clip, Generalization Aware Compression and Geometry Preserving Continual Learning for Vision Language Models on Edge Devices. The goal of this work is to enable geometry preserving compression and continual learning for vision language models on resource-constrained edge devices. The problems are twofold. The first is that we know that compression methods can compress the model to smaller size, but some methods will destroy cross-model alignment geometry, which is important to enable zero-shot generalization. The second problem is that continual learning addresses the catastrophic forgetting, but it cannot preserve geometric structure for transferring to unseen categories. So motivated by these two problems, we propose the clip. Our method includes two stages. We will introduce details later. First, we look at a little bit about the background. As we all know, vision language models encodes rich visual semantic knowledge, and it can enable zero-shot recognition while cross-model embedding geometry. But the problem is that vision language models are too large to be deployed on the resource-constrained devices. And the limitation of existing compression methods is that they compress the large vision language models, but they do not preserve pairwise embedding geometry for zero-shot generalization. And the limitation of continual learning is that they mitigate the forgetting problem, but do not preserve embedding geometry, often degrading zero-shot performance, despite they can maintain a very old category accuracy. So motivated by these two problems, limitations, we propose our work. Our work includes two stages. The first stage is generalization aware pruning. So the key idea is that it compresses the model. At the same time, it can preserve cross-model alignment geometry in the joint embedding space. The key insight of this method is that it filters using a unified importance score. This score captures sparsity, cross-model sensitivity, and multitask coverage. So we can see this equation. This is definition for this filter importance score. So this equation includes three terms. Each term captures a different aspect of why a filter matters. So the first term is a Fisher-Taylor term, which estimates how much removing a filter increase the zero-shot classification loss. And the second term is a cross-model term, which measures how much a filter contributes to image text alignment. We zero out the filter and measure the drop in concept similarity between virtual and textual embeddings. This is complementary to the first term. The first term measures classification loss. The second term measures alignment geometry. And the third term is multitask diversity term, which measures what fraction of task heads, including classification, retrieval, and grounding, are significantly affected by removing the filter. So basically, filters that matters across multiple tasks are important for generalization, so those filters are preserved. We prune the filters according to this filter importance score, and the next step, as shown here, is to recover the accuracy. So after pruning, we recover accuracy through null distillation. The pruned student is retrained to match the soft logits distribution, embedding concept similarity, and cross-entropy targets of the unpruned teacher. So the original model is a teacher and the pruned model is student. So after first stage, we can have a small student with a good accuracy. Now let's move to stage 2. Stage 2 is that the compressed model need to learn emerging categories from the unlabeled on-device data when they deployed. At the same time, it need to have a good balancing, like balancing plasticity, stability, and geometry preservation. So in the continual learning, rather than transmitting raw images to the cloud teacher, which will leak some user private data. So instead of to do that, the on-device student process each input through its first few layers, like first 6 layers, and generating intermediate embeddings. Then this embedding is into the cloud teacher. The teacher will continue processing through later layers, like layer 7 to layer 12, and it returns alignment layer activations. Then, for efficient on-device updating, the student receive this alignment layer activations, and we insert LoRa adapters. So only these LoRa adapter parameters are trained. Everything else is frozen. So this can keep the number of trainable parameters very small, at just about 0.1% of the total trainable parameters. So this can make the updates feasible on the edge devices. Then the training objectives, as shown in this figure, it combines 3 terms: the MMD geometry loss between teacher and student activation distributions at allied layers, and a traditional non-decision loss on the soft logits. And the third one is a EWC regularization term to prevent forgetting. So the goal for the second stage is that the student can learn the new categories at the same time without forgetting the old categories. So we can look at evaluation. In evaluation, we use 2 data sets. The first is CVPR, the second one is the tiny ImageNet. On each data set, we split them into 2 parts. On CVPR, the first 5 classes are classified as task 1, then the later 5 classes are task 2. Similarly, on tiny ImageNet, the first 100 classes are task 1, the later 100 classes are task 2. And we use we compress the model on task 1, then in continual learning, we let the model to learn task 2. So task 2 are the categories the model never trained with. Now we can look at the results. This is the results on CVPR. The upper figure shows the results on compression. The lower figure shows the results on continual learning. So we can see the upper figure first at a compression ratio about here 37. Our method achieves the highest task accuracy and all class accuracy. And we can look at the lower table. That's the stage 2 results. Z-clip is our method. It achieves the best task accuracy, about 76%, and zero forgetting. Here is 0. In comparison, we can see the baseline, the fine-tuning. The fine-tuning suffers significant forgetting of about 28%. So the accuracy for task 1 reduced to 46. Originally, it's about 76. And for this, EWC is a learning without forgetting baseline. It can control the forgetting. Here the number is low, but it achieves a lower average accuracy on task 1. Now we can look at the results on TinyImageNet. So same thing, the upper figure shows the compression results at a compression ratio of 12.9. It achieves the best task 1 accuracy and all class accuracy, outperforming all the baselines. And on the lower table, it shows the stage 2 continual learning. Our method achieves the highest task 1 accuracy and zero forgetting, outperforming EWC by about 3% on task 1. And at the same time, it maintains a higher average accuracy. And fine-tuning similarly suffers significant forgetting. The forgetting forgot 42% accuracy. So the accuracy of task 1 reduced to 6%. This is one of the application study. So this UMAP projections shows visual imbalance for 2,000 samples. On the left is a teacher. So we can see it has tight, well-separated clusters for all 10 classes. In the middle is a tiny clip, the best compression baseline. We can see the clusters are more diffuse and overlapping. The right figure shows our method. So compared to the baseline, it recovers a little bit. It recovers tighter and better separated clusters compared to this baseline, but still worse than teacher. And we also measure some inference on hardware. So this table shows the inference latency and memory footprint measured on a single CPU and an NVIDIA GPU. So the result is that on Sapphire 10, our method achieves a 19.3 CPU speedup and 36.7 times memory reduction. And on TinyImageNet, it achieves a 6.9 CPU speedup and 12.9 times memory reduction. So the compressed model can fit in with the RAM budget of the edge platforms like the Jetson Nano and modern smartphones, but the original teacher model cannot be fitted in those resource-constrained edge devices. So the conclusion for this work is that we propose a framework. It's a two-stage framework that can preserve cross-model geometry during both model compression and on-device continual learning. It enables new category adaptation without forgetting. And for compression, it achieves the good compression while retaining zero-shot transfer capability. And for continual learning, it actively restores cross-model alignment geometry during the on-device adaptation. So in summary, in total, it achieves zero forgetting on Sapphire 10 and TinyImageNet. In comparison, the baselines suffer up to 43% forgetting. So thank you.
Thanks a lot for the presentation. Do we have some questions on site? Okay, probably no. Then we're moving to the last talk. RGB is almost all you need, estimating soil parameters using Terramind. And this is actually an interesting example of the fields where you might eventually need to come up with efficient models. Yeah. efficient models for that can be deployed on satellites. Yeah, that's also an unexpected, field, an unexpected problem. Yes, we can see the slide.
Okay, right now.
And we can hear you.
But I can hear myself too.
Yes, for some reason we can. George, can you disable? Can you mute? Probably. George, can you mute your laptop?
Okay.
Yes. Okay. Yeah, probably just because George's laptop is presented is sharing the screen with participants on site, so maybe that was an issue.
Okay, maybe right now. Can you hear me?
Yes, we can hear you. Everything's perfect.
Okay. Oh, I lost my here. Okay. Hello everyone. My name is Agata Viata, and today I would like to say a few words about our experiments about determined and estimating soil parameters. Of course, on the beginning, I would like to say something about motivation and background. We know number of people is higher and higher, so we as a people need more food. Agriculture has still the same part of earth, so it is difficult to extend it. So we need more smart solution in this area. Right now, we have a lot of problem with traditional approach, like only information about per image, per whole parcel. We lost a lot of information from the spatial areas, and also it is very difficult to scale traditional approaches. So a few years ago, engineers at KP Labs company thought about Earth observation and about their own satellite. They create a satellite, Intuition 1, and one of the goals of its mission was precision agriculture. During the preparation of this mission, we organized Hyperview Challenge. This challenge was focused mostly on hyperspectral imaging and prediction of 4 soil parameters. It was very popular because we had more than 150 teams on the board during this challenge, and it is permanently open, so you can try if you want. But we have data, and I think about it that it is difficult to have access to the satellite and hyperspectral optical instrument for the farmer. And I thought that maybe some of this information is also available in the RGB image. So a few channels from the hyperspectral cube was extracted, and we applied a foundation model. Before it, a few research hypotheses were figured out. It was about spectral efficiency, statistical importance, operational robustness, mobile and edge accessibility, and of course, democratization of precision agriculture. Like I said before, we have got on the plate Hyperview dataset. It is dataset where we have spectral range between 400 and almost 1000 nanometers. We have got 150 bands, and we have got what is the most important, frozen data splitting. So it is easy to compare the results of different experiments from different teams. We can do this in easy way. Our dataset meets Terramind. Terramind is foundation model which were prepared by ESA, IBM, Jülich, and KP Labs company. And this model based on Sentinel-2 dataset. So as input, we have got 12 bands, and we can classify, segment, or predict something. And in this case, it was a regression task of prediction the soil parameters. During the experiments, we tested whole Terramind family models. The first one, Tiny, is the smallest version, and it is dedicated to the edge devices. The second one, Small, is a lightweight model. It is something bigger than Tiny, but it is dedicated for the task where we have a problem with balance. The most popular version base, it's a standard version designed for the air preservation problems. And the last one, the most advanced variant, Large. As adapter, we used 3 different heads, which are popular in the regression task area. The most, maybe not the most, but one of the important things for this task was band selection, because, like I said before, we have 150 bands. In case of the Terramind, as input, we can put only 12 bands. So we decide to find the nearest bands from the spectral hyperspectral cube to Sentinel-2 bands. And 3 different scenarios was tested. The first one was focused on the whole available bands from the hyperview, which can be correlated to the Sentinel-2 dataset. And the second one scenario was only RGB channels, and the last one, third, was RGB channels with near channel, and because sometimes it is available in case of the edge sensors. And evaluation was performed using Hyperview score. This score based on the mean value of 4 errors for our soil parameters, and we observed that Terramind large version for 4 channels achieve a Hyperview score, which is similar, like in case of the whole available spectrum. So we can say that it is big success. What's more, in case of the 3 channels, only RGB, the results are similar. So we can say that using RGB image, it is possible to predict soil parameters. Statistical significance was also calculated, and we observed that in case of the large and base models, there is no significant difference. So it is possible to use smaller version of models to evaluate of farms. We also calculate Blunt-Altman plots and interclass correlation coefficients. Observation, the most important information is that for the bigger models, it is easier to obtain better results, but the shape of different parameters are similar for whole models, so we can use also smaller version too. Also, it is important to remember that sometimes it is difficult to obtain clear only for soil pictures. So if we have a smaller number of bare soil pictures on the image, we still can predict value of soil parameters. Examples of images which was used in the experiment. And we can say that our research hypotheses were confirmed. So maybe in the future we can create kind of the application for the mobile phone which can use a Terramind model. Thank you very much.
Thanks a lot for the presentation. Yeah, so do we have any questions? Yeah, probably no more questions in the room. So yeah, then thank you, and thank you for this interesting talk from an unexpected field of science. Okay, so with this, we come to the end of the workshop. Do we have any questions in the room? George.
Sorry?
Do we have any questions in the room? So if the guys...
This doesn't appear to.
Okay, good. Then we come to the end of the workshop. I hope that you found some interesting material and hopefully learned something new. And yeah, so if there are no further questions, then we stop here and hope to see you all in the next mobile AI workshop next year. Okay, thank you guys. Bye.
Thank you, Andrei. Goodbye.